A very good afternoon to you in Shanghai, and hello to the rest of you around the world, and welcome to the session where we talk about new technologies that we have seen emerging in the last couple of years, really, that can help battle and combat food fraud. The first talk will be an overview talk on setting the scene on what the non-targeted is and how it works. And then we'll have five more distinguished speakers that will talk about different aspects on the same subject. So we'll start with the novel food safety testing application, benefits and risk. And let's first look at the challenges that food industry is facing. We have here food safety aspect that we've always been dealing with. So that could be the mitigation of unintentional changes to products and recipes, accidental contamination with pathogens. François will talk about that. And then we have, of course, the situation where you have a food defense, where somebody wants to do intentional harm to a product in order to bring harm to the company, or food fraud, where the motivation is economic gain. And when we just look at the number of products or the number of adulterants that are known for product, it's quite amazing. So for meat, for example, we have 55 known adulterants, and the emphasis here is on known. So there are presumably many more unknown adulterants. Similar for olive oil, we have around 70 to 80 known adulterants for olive oil. And for milk beats it all. So in 2019, when I did that query for the first time, and this information is coming from the Discernis database, I found 168 known adulterants. When I asked that to be done again a couple of weeks ago, it was 225 for milk alone, and those are only the known adulterants. So this is where the problem comes. If you perform analysis for a potential adulteration of milk, how would you detect all possible 225 known adulterants in an economically feasible fashion, and potentially also those that are unknown? And with targeted methodologies, that is simply not possible. I will give you a couple of examples where food fraud is quite obvious, and different scenarios. One of my favorite ones is the example of the olive oil from Italy. So this is an example from the 2014-2015 harvest. There were 222,000 tons of olive oil produced after the harvest. The Italians themselves in the following year consumed 521,000 tons of olive oil, just the Italians. And miraculously, they still managed to export a whopping 208,000 tons of apparently Italian olive oil. And you can do the math yourself. The figures simply do not add up. Now, some of you may say, well, maybe they have imported. Well, if you check the import number for olive oil to Italy, it is actually very low. It's in the 10,000s. So it still doesn't match. And that means that there is food fraud ongoing, there's adulteration ongoing. And this is when we developed a system where we looked at a screening approach using mass spectrometry. And we looked initially for more than 500 different data points that could be indicative of fraud. We discarded 500, we left with 63, and those were then giving us some indication if an olive oil was authentic, if it was from Italy, if it had been adulterated. So here, that was the first application of non-target methodologies that we developed for extra virgin olive oil. Now we have a example of honey. Honey is another product that is often traded at high prices, and especially when it comes to Manuka honey at very high prices, and there is a small volume produced. So honey has been known to have been adulterated. In the early days, it was with so-called C4 sugars. So that is, for example, corn sugars or cane sugars. And that was until scientists developed a method to detect the adulteration of cane sugar. So then you found that there was adulteration with C3 plants. And it took a while to develop a method that allowed you to detect not only the adulteration with C3 sugars, but also, for example, with C4 sugars, but also the adulteration with C3 sugars, for example, from rice or from wheat. And then what we have seen, and the fraudsters really got smart, they developed tailored syrups. They sold at very low prices. So that's a very great incentive for committing fraud with honey. So here you have tailored sugars, and when you look at the platforms, you can actually see that the producers state which of the analytical methodologies they pass. And here it says, for example, if you test for C3 or C4, they would pass the test. So you can see that there is a constant catch-up between the fraudsters and the scientists to develop methods that allow them to detect the fraud. And here is another example for dairy products. And already mentioned, you have 225 adulterants known to date. So here we looked at Parmesan cheese, one of the other high-priced products. And we found that there was sometimes milk used that was not from that specific region in Italy, but from a different region. And we, again, developed a method that was based on LC-MS. And we published that, so you can find all the details in the paper in MDPI in Foods, where we described how and what we did. And we're going to skip that slide. So how did we do that? So as I said, the problem with the adulteration is the fact that you have too many adulterants to be tested individually. So you need a different approach. And that different approach was the non-targeted screening methodology. And on the left-hand side, you see what it would look like when you have a targeted screen. So you may be looking for specific pesticides or specific mycotoxins, and your mass spectrometry or other methodology may easily identify them. But for the non-targeted approach, what you basically do is you generate a profile with so-called reference samples, and we're going to look at that in detail. So here, this is an example where you have several reference samples, and they all have slightly different profiles because there is a natural variability among each of the samples. So they are then being put in the database, and the database basically calculates a common profile. That is a profile that goes across all the different reference samples that you have. And there you see the common profile. And then you start testing samples against that. So here you have sample 1 and sample 2. And when you look, sample 1 perfectly matches the profile. So the chance that you have an adulterant in that is significantly lower as if you were testing with targeted methodologies for 1 or 2 different adulterants. Now, if you look at sample 2, you can see that there is a peak that is not matching the profile. And that is really the key aspect. If that appears, then you have a good indication that there might be adulteration, because again, there could be an indication that somebody has added something into the sample, but it may also be just an indication of a variability that you haven't captured in the original reference sample. So you would have to go and investigate, and this is where the targeted methodology comes in again, because here you need to identify what that, excuse me, what that peak is from. So this is where the targeted methodologies and the non-targeted methodologies play hand in hand. So the targeted is used for confirmation, whereas the non-targeted is predominantly used for screening. And examples are NIR and FTIR, and Steve Holroyd is going to talk about that. We have NMR technologies, MALDI-TOF, and LC-MSM as the two that I was talking about. But then you have a similar approach, and Francois will be talking about that in his presentation. We have that also on the DNA side, so not just on the chemistry side, but also on the biological side. And today, for example, or yesterday, we asked, is it horse? Is it beef? Is it pork? Now, with the non-targeted approaches, you can ask, what is it? So it gives you a much, much wider range of options that you can then answer using that specific technology. And similar for bacteria, you have the question a couple of years ago was, is it Listeria in 10 grams? And today is, what is in there and how much is in there? So the non-targeted technologies really give you the option of getting significantly more information and even beyond the known ones that you have in your database. And with that, I'm going to conclude my first part of the presentation. Most of us will have a second part. So I'll stop here and introduce the second speaker of today, which is Steve Holroyd from Frontera. And Steve is a principal research scientist within the food structure team at Frontera Research and Development Center. He has 25 years experience in the implementation of infrared spectroscopy in oil and gas and pharmaceutical food applications, with over 50 publications in peer-reviewed journals, and is the author of 3 book chapters. He is currently president of the New Zealand Near-Infrared Spectroscopy Society and a member of the Toastmasters International with a passion for scientific communication. On behalf of New Zealand, he is invited with a variety of analytical standards development organizations globally, including the International Dairy Federation, International Standard Organization, AOAC International, and United States Pharmacopoeia. He is currently the chair of the IDF Method Standing Steering Group and a member of the IDF Science Program Coordination Committee. Steve has a PhD in chemistry from the University of Auckland, New Zealand, and a postdoctoral experience at Cambridge University. Over to you, Steve.
Thank you very much, Bert. I appreciate the introduction, and good afternoon, everyone. Just let me know when you can see my screen, please, Bert.
Yeah, if you can put that in presentation mode. Perfect.
I have, okay. Thank you. So I'm going to talk about non-targeted applications, and really where Bert has introduced the topic in a general sense, I'll specifically focus on milk quality analysis and how non-targeted applications using a specific analytical technology can be deployed in this area. I'll cover the dairy value chain as a bit of background and talk about how analysis fits in. Then I'll talk about food safety, quality, authenticity, and screening, the logic behind doing these processes. And I'll spend most of the talk talking about the application of mid-infrared spectroscopy for routine analysis, and then how it's the development and application and challenges of using non-targeted methods with this technique. And I'll leave you with a vision of the future about how we can use non-targeted methods and the things that are essential to make them successful. This is a schematic of the dairy value chain. We have farmers milking cows. The milk is collected and taken to factories where it's turned into products. That's a Frontera 25 kilogram bag of milk powder. And products such as that, which are widely used as food ingredients, are sent all around the world and ultimately end up in products in front of customers and consumers. Analysis happens at virtually every stage. We analyze the milk as it's for farmer payment purposes. We analyze the milk we have in factories before processing, during processing as well, and when we're finished making our products. And then all around the world, again, our customers and regulators, they also do analyses of the products that we produce. So there's a lot of analysis that underpins this chain. If you look at that in a more schematic view, and especially with a focus on quality control and safety and quality, we have the chain across the top of this screen. And we do things up front, for example, to prevent economic adulteration, where I'll focus the talk today. We also do a lot of routine compositional and microbiological quality testing. And we're also obviously interested in the detection and prevention of contaminants and residues as well. Further down the supply chain, we do work to improve process quality and ensure that the supply chain has good integrity. And all these parts are parts of the jigsaw that's really important to ensure safe and nutritious products are delivered to our consumers. Just also a bit of context around the melamine adulteration of milk powder in 2008. This is where melamine, the compound shown here, a highly nitrogenated product, was deliberately added to infant formula to increase the apparent protein content as tested by the Kaldal reference test. The Kaldal reference test measures nitrogen as a proxy for total protein. It was a very serious food safety incident. It really changed our perspective of food safety globally. And it prompted a lot of interest in the use of non-targeted applications to detect adulterants and contaminants, and especially future adulterants that we hadn't really thought of and we needed to be prepared for. This is a slide borrowed from our colleagues at US Pharmacopoeia, and it illustrates well an approach about how we do food safety and food authenticity. We have a universe of all the ingredients or foods we're dealing with. Bert mentioned honey and milk. Obviously, we deal with dairy. Some areas have greater risk when we do a risk analysis. Some of those parts have the greatest risk. And then we have a short list of things that of ingredients or foods where there's unacceptable risk. And we need to have steps to understand the risk around this. We assess the vulnerability, we assess the impact, weigh the overall risk, and develop a mitigation plan. And really importantly, the smart testing, for example, non-targeted approaches, is a really important part of our toolkit and our mitigation plan. Just to illustrate economic adulteration, in this case with milk and adding melamine, this plot shows the apparent protein on the y-axis and the amount of melamine added, which, as mentioned, artificially inflates the apparent protein. If you add about 100 parts per million of melamine, solid melamine into milk, you get about 5% additional value. If you add 1,000 ppm, so 1 kilogram into 1,000 liters of milk, you inflate the apparent protein by about 20%. So there's a significant economic driver to add adulterants. And this also gives us an idea of the risk and the sort of levels we might see if we're looking for an adulterant such as melamine or some other related compound added for economic gain. It's not going to be there at parts per million, low parts per million or parts per billion levels. It's there at significant amounts to give economic gain. So it gives us some idea of what sort of targets we could aim for. And then we have practical approaches. We've got a business like Fonterra that collects milk in many countries. We've got to manage the risk associated with accessing a global milk pool, have the right tools and business support systems. We've got to be able to assess someone dropping off milk in one of our collection points in South America, in a donkey like that, or a modern milking shed in Tasmania in Australia. What are the appropriate systems we have in place to do safety and quality in those very different locations? We have to consider things like where to screen for adulteration. We can't test all the milk we collect. We need to be selective. We've got time and budget around this. And if we think about the value chain, and this is slides from our milk collection process in a country like Sri Lanka, we have milk from often an individual cow, people cycling to a milk collection point, small volumes of milk being combined and collected and ultimately processed. And if the bottom plot shows the concentration of a potential adulterant, it's going to be added at some point after the cow is milked. the concentration may peak at a certain place, maybe from a single supplier. As that milk is combined with milk from other suppliers that is not adulterated, the apparent adulterant will be diluted and may become more challenging to detect. So there's a time, and then possibly with processing, the adulterant concentration may increase. But there's a suitable time to test is quite close to the supplier. But there may be challenges around test costs and the logistics of testing that need to be considered. This is a quote from one of our colleagues in the University of Copenhagen from Søren Engelsen. If you want to detect food fraud adulteration, you're not looking for a single substance. You have to look more broadly. And this really is the genesis of non-targeted methods that Bert's referred to in his introductory talk. How do you, it's like a shape identification game. How do you identify this triangle from a whole lot of squares? But of course, reality is it's actually very challenging. The shapes are all very similar, and the information we get from chemical analyses can be quite complicated. So how do we translate a pattern recognition process into a business process that helps with our safety and quality program? This is where I'd like to introduce mid-infrared spectroscopy, which is what I'll talk about in some detail. This is a common approach for milk analysis. It measures milk composition, the fat, the protein, and the lactose in milk. There's a range of different instrument types that are available from a number of vendors, and they can be used in different environments. The top illustration here is a high throughput instrument in a central milk testing laboratory in New Zealand. That instrument can measure hundreds of samples per hour using mid-infrared spectroscopy. The bottom slide shows a similar instrument behind our colleague, but that's in Sri Lanka. It's a manual instrument, but using the same approach. And again, it can measure milk composition rather more slowly, but it uses the same principle of mid-infrared spectroscopy. And they're all rapid techniques for gathering information on milk using the technique called infrared absorption. This utilizes a band of the infrared, the visible electromagnetic spectrum, which is just beyond the visible where we see. And it uses mid-infrared radiation. You can see with those frequencies there. And the principle involves shining light through a sample, the sample obviously being liquid milk in our case, and then detecting what elements of that light are absorbed. There's a law called Beer's law that states that the absorbance of the sample is proportional to its concentration. So the greater the fat and the protein, the more absorption happens. And that allows us to measure quantitative amounts of substances in a sample like milk. This is the sort of trace we get when we do mid-infrared spectroscopy on milk. We have absorbance on the y-axis followed by a wave number, and the individual chemical bonds, the fat and the protein and other components in the milk absorb at different frequencies. This is about 100 different milk samples. You can see each one is different. And we use the term it gives a fingerprint for each individual milk sample that is subtly different. And mid-infrared instruments can gather these very precisely. And this is a very useful way of assessing rapidly gathering information on milk. Historically, mid-infrared spectroscopy has been used quantitatively, as I've mentioned, with instruments like this one for over 30 years. From about 2000 onwards, people have used it in a bit more detail, and from 2008 onwards, following the melamine crisis, there was a focus on adulterants as well. And currently, we're using mid-infrared spectroscopy to look at components like individual fatty acids, proteins, and also adulterants at concentrations in economically viable ranges. That's sort of 100 to 1,000 ppm. Mid-infrared spectroscopy is not particularly sensitive. It's not going to pick up contaminants that might be present at parts per million or parts per billion levels. It can't do that, but it can look for adulterants at potentially at economic levels. This is how the technique works. You measure one of those peaks or a number of those peaks in the spectrum that I showed previously. You construct a calibration, and this is of known absorbance versus the wavelength. You plot some sort of calibration curve where you've measured the values in a lab and you get a calibration. And then you measure a new sample and it's somewhere in between, and you use that calibration curve to assess the concentration. As Bert showed earlier, though, that's a targeted analysis. We're looking at a specific peak or range of peaks due to fat or protein, for example. With a non-targeted analysis, we wish to look more broadly, as Søren mentioned, so we use much more of the infrared information to guide us. This is early work we did with milk with non-targeted methods. We used some statistics called principal components. A range of normal milk samples with the green points in this two-dimensional plot were clustered around the middle. And when we deliberately added potential adulterants like melamine, cyanuric acid, and ammonium sulfate at certain levels, and under certain concentrations, they could be distinguished using the statistical technique to examine the infrared spectroscopy results, and we could distinguish them. We developed that further, and this is a schematic of how it works in practice. You define a range of good points using mid-infrared spectroscopy and statistics, and you say, okay, that a semicircle here is all the good points, and that we know that milk is reliable and good quality. We measure 2 more points. One may be within that space when we do the statistics on the spectroscopy. One may be outside that. The one that's inside we say is okay. The one that's outside may be abnormal. It's different for some reason. We don't actually know the reason, but we know that it is different and requires some further investigation. So the non-targeted methods, we gather a database of representative samples of fingerprints as we've shown here. The database can be quite large. It can be even global, potentially. It depends on the analytical technique and how widespread it is and what sort of variation we're looking for. We do some sort of statistics. As I mentioned, principal components, we define some groups. Then we measure a new sample and make a decision. And typically it's what we call a binary decision, a traffic light. It's either good when it's green or it's red and it's not. And we do further analysis. We may have an intermediate step, but typically businesses are quite simple. We prefer either a binary approach, good or bad. This is an example of where we've tested such an approach using mid-infrared spectroscopy. Each of these 120 samples is an individual milk. We've put a melamine in some of them deliberately, and the more melamine that's in there when we treat it with statistics, we generate a score, and the higher that score is. And you can see the red samples, at a high level of melamine, we can detect it with this non-targeted method. There's variation in the blue samples that are not adulterated, some variation, and we can draw a threshold somewhere to say if you're above that, we can detect melamine. You'll observe some samples as well, of course. They have melamine at a low level. We can't observe that. So we can get some sort of limited detection with a non-targeted method for a specific adulterant. And we can use this routinely as well. This is an application called the abnormal screening module. It generates a score on each individual mid-infrared spectrum. This is 2,500 or so mid-infrared spectra from routine screening in New Zealand. You can see this variation, and there's one sample that does stick out above the others and perhaps above our threshold. When we investigated this sample, it was found that the farmer had actually inadvertently cleaned his vat out on the farm and left a little water in that. It wasn't a food safety risk, but the milk was diluted to a small degree. The non-targeted test could pick that up, and we were able to take corrective action, while it was not a food safety risk. An example is with urea adulteration in milk, as well, using these non-targeted approaches. Urea is commonly available, it's very soluble in milk, and it's also naturally present. You add a kilo of urea to 1,000 litres of milk, you get about a 0.3% increase in protein. And this can be detected using non-targeted methods. We can illustrate this here. If we use this ASM approach again, we do mid-infrared spectroscopy, we do statistics, we deliberately add urea to milk in those concentrations, and the ASM number is increased the more urea that we add. And we can draw a threshold here and again determine a limit of detection using non-targeted methods for a specific compound like urea. Some of the challenges we can have that are specific to mid-infrared data, what's the reference data? Is it quantitative or qualitative? We're good as analytical chemists, we know a lot about reference data and standard deviations of testing. If you're just saying good or bad, how do you assess that? What is your reference data? Infrared instruments need to be stable over time to approach this. We've had some incidences, I won't dwell on this too much, but we see a step change in these ASM results. That proved due to instrument instability, which we could correct, but we needed to know about that. You also need to make sure the instruments are standardized, reading the same sort of results. Some of our colleagues in Belgium have looked at this, have done some great work in understanding the standardization process for infrared instruments. I've put the reference there. And you need to be able to integrate your data and make business decisions as well with these techniques. Some challenges of non-targeted methods in general as well, and this comes back to a wider swathe of potential applications. There's confusing terminology in the literature. What's authenticate and discriminate, false positives and false negatives. Risk tolerances, How does a business deploy these methods? What's your risk tolerance? Do you understand how well the method works versus your tolerance for risk in a specific location? How representative is your reference or your calibration models? Do they truly represent all the milk, in our case, that is good? And how do you validate a non-targeted method? I'll give some indication of that, and I'll deal with that in a little more detail. And how do you choose adulterants? If you're going to test a non-targeted method, what do you do? This is work I've published in conjunction with a colleague, and you can validate non-targeted methods with deliberately spiked milk. Here there's a range of different potential adulterants and different colors, and we tested over 2,000 samples. We test for factors like sensitivity, and that's the ability to correctly recognize unacceptable samples, and specificity, which is the ability to correctly recognize acceptable samples. And these are defined. I won't go into detail again. I'll talk a little more about this in a subsequent presentation. But you can see against different potential adulterants, the mid-infrared screening test, it works really well on some potential adulterants and not as well on others in terms of assessing its sensitivity and specificity. And the paper in the International Dairy Journal we've referenced there gives a lot more detail about how we reach those numbers. And this is how we approach a validation of a non-targeted test for targeted adulterants in liquid milk. I'll talk again later on in the session about guidance around how we do that in conjunction with our colleagues at US Pharmacopoeia and the Food Chemicals Codex. We've put a lot of work into giving guidance around how you deploy these, not just for mid-infrared spectroscopy, but for a wide range of analytical technologies. Bert mentioned the GCMS, mass spec, NMR. It can be applied in many different cases. And typically we also see, of course, I've talked about non-targeted methods. We need a hierarchy of methods for food safety. We need screening methods that are rapid and easily deployed in different locations. Mid-IR can work in this case. You could have perhaps as a second tier, semi-quantitative use of liquid chromatography and mass spectroscopy. And you also need in many cases, confirmatory methods, international standards to be sure that you've actually to verify your results. So really important to have hierarchy of methods and a suite of appropriate methods that depends upon your business and your geography and your risks. So a vision of the future here, we see a wide range of mid-infrared systems, the accuracy dependent on the value chain where it's deployed. Non-targeted models using this full spectral region. We could use targeted models. We understand the cost versus accuracy and it's appropriately validated. We have this hierarchy of methods and we use with guidance from international standards organizations that I've listed there to give us our ability and maintain our ability to deliver healthy and safe nutrition globally. I'll just finish with some acknowledgements here. My colleagues in New Zealand, Milk Test New Zealand and at University of Auckland, colleagues at FOSS also and ALA and US Pharmacopoeia as well. We've worked with a number of different people. Food safety is truly an international effort and it's well illustrated there. That concludes my presentation. Back to you, Bert. Thank you.
Thank you very much, Steve. And we're continuing now with François Baudichon, and François holds a master's degree of general microbiology from the Pasteur Institute in Paris. After 15 years working for a major dairy company, including Nestle, Danone, and Savencia, and a confectionery company like Barry Callebaut, he now works as a principal consultant for food safety, microbiology, hygiene. And since 2018, he's also affiliated with the University Cattolica de Sacro Cœur in Placenza in Italy, in the Department of Food Science and Technology for Sustainable Agri-Food Supply Chain. François is delegate of France at the IDF, the International Dairy Federation, since 2010. And he represents IDF at the Codex Committee for Food Hygiene, CCFH, and in different ISO TC35 SC9 working groups. Most recently has been chair of a dedicated expert group within ILC Europe focusing on processing environmental monitoring in low moisture food. He is presently the action team leader within the IDF on processing environmental monitoring in the dairy industry. François, over to you.
Thank you, Bert. So what I will present Ni Hao Beijing. Unfortunately, I cannot attend physically the presentation. Time is a bit complicated right now, but hopefully we will be able to meet in presence next year in Shanghai. I will talk today about next generation sequencing for the food industry and how this is a new paradigm for microbiologists and how this changed the limits of the current tools we've been having, and it opens us a new level of evidence for investigating either the food per se, but also as well having more information on the food products. I will, since I'm the only microbiologist around the talk, I will split the presentation in two. And the focus today is really to explain that molecular microbiology helps us knowing the unknown. In microbiology, there are far more than meets the eye that what we actually know. We have a new set of tools that give us a lot of information. Some we do not completely understand yet. Some we are also not ready to deal with. And the point is, how are we going to switch from culture-based microbiology to this molecular microbiology? This is something that we've been discussing for the past 20 years, that traditional microbiology is dead. We will have a new molecular microbiology, but still, even these tools are available, we are still working on these traditional techniques. So that's always the question, so to know where we are going to go beyond culture-based microbiology. When we speak of the founding fathers of microbiology, we often refer to Louis Pasteur or Robert Koch. It depends whether you're French or German-oriented in your training. And when you come to the plates we're using, we often call them Petri dishes coming from whole-use Petri. In fact, this were two assistants from the department of Robert Koch who worked on this field, was Walter Hesse, and more specifically his wife Fanny Hesse. She was the one who discovered that it was better to use agar rather than gelatin in order to maintain solidified state of the Petri dishes at room temperature. So when we speak of culture-based microbiology and we refer to Pasteur type of Robert Koch type, in fact, there is a woman behind. And history should be remembered. That's indeed all the techniques we use today, mostly in microbiology, was coming from the idea of Fanny Hesse during lunch, where she explained to her husband why her cake was more solid than the traditional one, because she was using agar imported from the United States. Growth on media in microbiology is something that we use a lot, but there is a big issue behind. It is biased by design. We often hear people saying that they did total plate count, but that does not exist. This is not possible. Even the ISO standard, which is used for plate count agar, is for total sort of mesophilic aerobic count, which means that as soon as you use a certain temperature for incubation, you select a part of the microorganisms, and depending on the type of media you're using, you're selecting another set. And depending on the physiological state, it's not all microorganisms will grow. So as soon as we use culture-based technique, we only see a little bit of the puzzle. And sometimes we take decision based on techniques which in fact only give a part of what we need to know. Something which has popped up a lot in the past 20 years is what we call VBNC, viable but non-culturable cells, which cannot be enumerated. There is a physiological condition behind that we call the bacterial dormancy. This is a condition in which the cells are viable, they are active, but they do not grow. They are resistant to cultivation by routine growth medium. So, and whenever you count, the unit is colony forming units, which means that cells that cannot form colony will not be counted. And the choice of the substrate and formulation will have an impact and oriented which organism will grow. So it's only a limited and oriented snapshot of the microbiota of those samples. And when you look at the initial lectures, initial publications in microbiology, they really saw that it was quite simple and there was not so many microorganisms. But in fact, they discover more and more than VBNC has a lot of relevance. that there's a lot of publication about this one. People thought at first that, yeah, VBNC is an issue, but if they do not grow on agar media, that's not an issue because they don't have any impact and won't be harmful. But we've seen that for foodborne pathogens, even so you cannot cultivate them, or even the growth media is too selective and do not help for resuscitation, there is still a health potential, health deleterious potential behind. So we need to have better techniques in order to really be aware where are the pathogens if we found them, and to ensure general public health at the end of the day. So culture dependence, how do we shift from this? And one of the points which was mentioned is to go for another expression of the presence and the viability of the microorganisms. And that was something that really popped up in the late 90s, in the early 2000s, which is becoming more and more topic of the day in microbiology. That's to use culture independent nucleic acid-based methods. And they help us finding more microorganisms depending either on the state or even type of microorganism for which we don't have a good agar media, or being more direct in being more specific. One of the issue we have with microbiological culture media is sensitivity and specificity. And a very hot topic, very classical name that you hear at every source and sometimes misused is the microbiota. Microbiota is coming from ancient Greek origin, small and life. So it's microbiota is the living organism of an ecosystems of a particular area. So there is a lot of focus on the gut microbiota with all the science going on with probiotics. We also discovered that there were more microbiota presence in the human rather than in the gut. In fact, there are a lot of area that of our body that we thought were sterile and it's not sterile, which defined human as a allobionts. We are not only characterized by ourselves, but also by the organisms that are living without us, depending on the skins, on the guts, in the ear or in the nose. And there is a misfit between microbiota and microbiome. And microbiome is mixture of English, Greek, and it is used to explain the totality of genomes of a microbiota, which means that the microbiome expresses the genomic potential of a global population. And this is valid for a food product, this is valid for beverage, this is valid for water. And the microbiota can be targeted when you use specific food cultures, but can be also naturally present with the common soil flora. And it can be also used to characterize specific food products, and particularly difficult to mimic. So when it comes to microbiome, so we won't go through all the dates, but what is very important in that there was a huge acceleration in the past 30 years. As you can see in 1991, the theory of the holobiont, which means that we are inheritance of also in our phenotype from the different microbiota we have on us. And there are more and more study going on, which really express the need to characterize the microbiota when you want to consider a global microbial risk assessment. This is something right now which is under consideration from the FAO and WHO with in discussion with GEMRA. We also have a position in Europe from the EFSA that microbiome should be taken in consideration when it comes to the pathogenesis of different microorganisms of concern, because we are not all equal when it comes to infection. Some of us are more resistant. This is also something we have seen very recently with the COVID-19 disease, is that a healthy gut microbiota can protect you better than the dysbiosis. So that's pretty important to consider the role of microbiota. There are different methods in order to assess the microbial functioning. The first point that it's always starting with is the potential. Who is there, which is the microbial. So you have a look of the global microscopy of all the culture mix when you can see all the cells present. The second question you ask yourself once you know that you have a microbiota presence and a population is what they can do. That's their potential. And this is where you switch from the microbiota to the microbiome. When you look through the DNA with different techniques, which genes are present, which is a pangenome, core genome of different microbial species, what is shared by different microorganisms, what is specific to one family of microorganisms versus another. Once you know who's there and what they can do, are they really active? And then that's a microbial function that you need to have a look for. It's an active metabolic pathway, the transcriptomics, proteomics, or metabolomics, which means from the RNA, the protein, and what's going on with the metabolite. You need also to characterize the catabolite and anabolite because microorganisms interfere with the food matrix. And depending in the food matrix they have, they can be opportunistic pathogen, they can be, I can have a positive role. So it's pretty important in your global assessment to consider not only the microorganism or the set of microorganisms, but as well the niche where they are living. And all this science right now is booming. If you see on the publications, this is going in a lot of direction. And there are a lot of potential applications when it comes to food safety, to characterize more than specific pathogen of concern, but having a look at for which population is present and what's its impacts on your final assessment. And this is something we will discuss slightly later. I'll let you digest this first concept on switching from focused on specific microorganisms with techniques which can be sometimes cumbersome and giving you a bias, to looking at the global frame. And now I've seen that there is a huge diversity of population, and what can I do with this? And I'll come back later on the topic. Floor to you, Bert.
Thank you very much, Francois, for the presentation. So we switched from the chemistry technologies to the microbiome and microbiological technologies. And now we're switching over to food law. We're going to do that with Cesare Ferraro. He is a food lawyer based in Italy and founder of foodlawlatest.com, an independent law firm and a food law blog. In addition to labeling compliance services on over 90 countries and food law advice, he regularly provides assistance to clients in relation to crisis management, food safety issue, food fraud investigation, and import-export requirements. Through partnerships with technical experts and other international advisors, he proudly worked at the intersection between food technology, law, businesses, social sciences, and building bridges between different sectors to deliver a strategic and actionable advice. He's a well-recognized speaker, and he is involved in several scientific activities and committees. He is teaching at LUISS, LMM in food law in Rome, at a master in food law and food safety at the University of Alma Mater in Bologna, and he's a guest instructor at the Michigan State University Institute for Food Laws and Regulation. Cesare, over to you.
Thank you, Bert. I'll share my presentation. Thank you for this very nice introduction. I'll switch to presentation mode. Okay, from the beginning. And here we are. Thank you very much for the introduction. So you said all. I'll skip the first couple of slides where I present some numbers about who we are and what we do. What's important to stress is that when we speak of the legal proof that an analysis might have, we are speaking of situation mainly when there is a controversial issue, when we have litigation, where a situation where we are in courts. There might be a civil court or a criminal court because I had a food safety problem, and in that given country there are criminal sanctions for those situations when you harm a consumer, for instance. But what is important to stress is that litigation is a very different thing in different countries, okay? There is not basically a country that is working exactly like another one. So today we try to extrapolate some general principles from what I saw in my experience in Italy, in Europe, in US, in different countries. But you have to keep in mind that Europe is mainly governed by systems called of civil law, while US, UK, and English-speaking countries by common law, which is a different, really not just a different way to draft the laws, it's really a different mindset where, for instance, the court cases have a major value compared to Italy or France, and China is totally different. So we try to extrapolate some principles that might help you. But if it's possible to give consultancy on food law and labeling in most countries of the world with the right expertise, it's really impossible, to represent clients in courts everywhere. It's a very diverse landscape. So please keep this in mind. The first part of the presentation will be about accreditation. What is the accreditation of an analytical method, and what are the benefits of the accreditation? The second part, in the conclusions, will be more about some case studies from which you can understand better what I'm saying in this first part, mainly. Okay, I will refer to Europe just to give you a glimpse about how we organize here, how we accredit analytical methods, but it's not such an uncommon scheme. Okay, in US it's not working, for instance, very differently, and I'm sure also in China, from what I read briefly, there are systems that might be comparable. But let's focus for a moment on the concept, the idea of accreditation, the definition. What is accreditation? Well, accreditation in the European system is the last level of public control over a conformity assessment system, is the softer level of public control. And we will see why we say public control, because most of the accreditation bodies are public entity, not private entity. This is important to understand for understand the European perspective. And usually it's a system that is efficient, especially for voluntary certification schemes, voluntary regulations, and technical standards. It's designed to ensure that the conformity assessment bodies, they might be conformity assessment bodies for laboratories, certification bodies of other type, like, certification bodies that assess if a company might be certified as organic or not, or respect certain standards in terms of sustainability and so on. So it's designed to ensure that conformity assessment bodies have the technical capacity to perform their duties in a correct way. So it's different from the certification. In certification, the external assessment confirms that the organization is in compliance with its procedures, so mainly with paper procedures. While in the accreditation, the assessment body confirms that the organization is competent to perform certain tasks. So it's not just about following procedures and papers. That is, of course, important, because if we don't follow the right procedures in technical activities, very often we arrive to wrong results. But is the confirmation that basically the laboratory, in this case, can deliver a useful and actionable and reliable result, okay? And the product is said in a very general way. This is true both for the analytical methods, but also for the reference materials for the labs, of course. For this reason, laboratories are accredited, not just in food safety, in all the sectors, according to an ISO standard, so a voluntary technical standard that has been drafted with the cooperation of different states and stakeholders. And this is a crucial factor for the customer to evaluate the competence of the laboratory. in the same spirit, the laboratories, of course, care a lot about the competence of the producers of the reference materials, because if you start from a reference material that is not reliable, of course, you will get a false result. Why is it important to stress that this is a meter to evaluate the competence of the laboratory? Because most of the countries in Europe did a step forward and basically said that, especially in fields that are very sensitive, like food safety or public health, if you are a company and you have to demonstrate that you are doing correctly, you are following correctly the hazard method, you are doing your testing, routinary testing, and all your activities, your internal control checks in a diligent way, you have to use by law, because there are specific provisions in certain countries, including Italy, in accredited laboratories and using accredited methods. This is a prerequisite to give legal value to the result of the analysis. Okay. If you want to use a laboratory that is not accredited, you can do it. Sometimes it might be cheaper, it might be better, even if you are able to evaluate their competence. There's nothing wrong in using a non-accredited lab. Okay, they might perform a decent analysis as well. But if you have a controversy with the competent authorities, with the controlling authorities, basically your analytical result will have nearly a zero value compared to the official testing performed by the public authority in an accredited lab and with an accredited method. The problem with not targeted analysis, as we will see, or these new areas in the analytical sector, is that it might be complex to get an accreditation or impossible, or there are no methods that are accredited at all in a specific sector. So this is the challenge today. What we do as companies to mitigate some emerging risks that might be about authenticity of food or other kind of risk, where we don't have accredited methods. Well, we have to try, first of all, to use the more reliable methods possible and to demonstrate to be, let's say, very detailed and also creative sometimes in explaining why those methods are working. Okay, also because they need, as we have seen, also a certain degree of interpretation. Okay, often are not methods that give you a yes/no answer, black and white, all the time. So it's we need to substantiate why we are doing some checks, how we do those checks, and try to be very persuasive if we have to defend a position. We have also a regulation that disciplines this accreditation system in Europe and gives some definition, like technical specification, that is quite obvious. Okay, it's a technical document that prescribes certain requirements that should be met by a product service, harmonized standards like ISO and standards, so technical standards adopted by recognized standardization bodies, and the definition of accreditation, of course. It is the attestation by a national accreditation body that a conformity assessment body meets the requirement set by those harmonized standards. So when you imagine the accreditation system in Europe, you have to imagine like a pyramid, okay, where you have some central accreditation bodies that accredit other conformity assessment bodies and other laboratories at national level, let's say, or a European level, and then going down laboratories at local level. The main principles that are set by this regulation are the following. And the first is very peculiar. We have one accreditation body per each European country, and we cannot have more than one. The idea is that they shall be public entity, non-profit activities, and there shall be no competition between national accreditation bodies in the same country. So the fear is that putting different accreditation bodies in a competition situation will create logics where the price prevails on the quality of the duties performed, of the service performed. So we want to avoid that. This is quite peculiar and has been heavily criticized by other countries outside of Europe, because there are regimes, for instance, US, where we have different accreditation bodies, not just one for the whole country, of course. And for those of you outside of the European Union, you have to keep in mind that Europe is not at all like US, but not even like China, that is a continent, okay, but is a unique country. We are still a bunch of sovereign states that put a small part of their sovereignty, of their power in the hands of the European Commission, but still retain their legal status of independent states. So in many areas, they do what they want in terms of legislation. For instance, we don't have a common system to administer justice, as mentioned. In each country, how a tribunal, a court is working is different. Accreditation is the preferred means for demonstrating the technical capacity of certain notified bodies in regulated areas. So the accreditation scope, to move to the end of the first part, is used in regulated sectors and voluntary areas, mostly to increase trust in these conformity assessment, and also to reinforce the mutual recognition of products, services, systems, and bodies that might be, in turn, when we speak of products, as exchange between different countries more easily, because you can rely on the fact that the same standard has been respected. So also if you have different legislations, you know that a certain device, a certain service meet certain technical specification. And just to explain better why it's so important, accreditation, to stimulate trust, let's think about surgeons. Would you trust surgeons if they do not operate according to precise standards and using instruments that are checked and guaranteed to reduce failures at minimum and keep you alive when you are, you have your belly open on the table and your heart beating outside of your chest? Well, probably not, I would say. The same goes when if you want to go to space today with, Elon Musk or Richard Branson, probably if you invest, I don't know how many millions to do a space travel, probably check that, they at least respect certain standards. But the same goes also in the other way. What if you are a surgeon and you have to operate a patient that basically have, 5% of chances to survive from a given situation without specific protocols and procedures that might help you to save the patient, but also to keep you safe from litigation if the patient dies, because it works both ways. My father-in-law had a terrible accident 2 years ago, and honestly, I was surprised that we found a surgeon in a public hospital that took the responsibility to do the operation at the head, because he fall working on the working place. He was doing constructions in his life. He hit the head, and the situation was really dramatic. Luckily, now he's well, okay, he's more than 70 years old, and probably the hit in the head has, accelerated certain processes in the aging, but he's perfectly fine. But in many systems, in many hospitals, I would say that a case like that would not reach even the table in the surgeon, in the chamber, in the operatory chamber, because it was too risky. Honestly, the situation was desperate. We didn't think really that he could make it. Mutual recognition, well, that's obvious, okay? I don't have to explain you how would be a nightmare, the situation without technical standards and accreditation. It's already a nightmare. When I have to charge my new bloody phone I switched from Huawei again to Samsung. I discovered that Samsung changed again the cable and the plug. So the European Union, for instance, is proposing to have common charger for phones at the moment, because Also, if we have technical standards, you know that there are technical situations where we have very different solutions to the same problem. So we have no standardization at all, and this might be complex to have. With this, I would say that I can close the first part. I will spend a few words more about lab organization in EU and the case studies afterwards. Bert, if you agree,
Yes, thank you very much, Chair. I think it's very good to understand what the risks are if you're working with a non-accredited laboratory, but also you pointed out, and I will pick up on that a little later, on the challenges of getting accreditation for such technology. So that is indeed very challenging. So we'll come back to you. Now we're going to continue with Dr. Bala Ganesan. He is the principal scientist at the Mars Global Food Safety Center, conducting research in metagenomics of foods and has been working with Mars for the past 6 years. Dr. Ganesan has extensive experience on applications of metagenomics in food safety and metagenomics and metatranscriptomics broadly in foods and extreme environments from his tenure previously at the Utah State University, where Dr. Ganesan was a research investigator for 8 years after obtaining his PhD in 2005. Gala, over to you.
Thank you, Bert. I'm going to share my screen right now. Hope it works. Just a second. Hopefully you can see my presentation now. And
if you click on presentation mode.
Okay, does that
work? Perfect, yeah.
Okay, excellent. So we have heard several different perspectives so far, which has been quite interesting to me. And I wish to assure my colleague, Dr. Francois Bergeschwan, who presented before me, that he's not alone as a microbiologist. I'm also a microbiologist by training. So, but today we are more focused on looking at a business case of how we can apply high throughput sequencing in food authentication. And so the process, I will have to say, is not independent of looking at the microbiota or the microbiome as much as looking at the matrix composition. So, but in order to help everyone understand what the business case is for, particularly for Mars Incorporated, to take a step in this arena, I want to go through some background information here. And if it takes too long, I will take a pause if Bert doesn't mind, so that we can review the rest of the presentation in the second half. We'll see about that. So, so just to think about that, I mean, we want to talk today about why quality is important to Mars, and what food safety management is in an industrial setting. And based on this background, we want to spend some time thinking about what kind of applications next generation sequencing can help us with. So quality is important to Mars because we are a big business. We have more than 130,000 associates, and the business has lasted beyond a century at this point. And it's a well-recognized brand with company with several billion-dollar brand products being sold in the market today, headquartered in McLean, Virginia. And it's one of the biggest private family-owned companies. And the business is governed by the 5 principles of quality, responsibility, mutuality, efficiency, and freedom, each of which have very specific definitions on how, and they guide how we operate day to day, both as a business, but also within the business in various functions, such as quality and food safety, research and development, and veterinary healthcare, pet care, various pet care products, various food products, and a lot. So at Mars, we believe that the world we want tomorrow starts with how we do business today. So what we need to do to make that happen is to have the best business practices that make the world a better place tomorrow. And to do that, we need safer foods, which means leading to the ideal of better food today and a better world tomorrow. So in the World Food Summit 1996, there was a statement made that food security exists when all people at all times have physical and economic access to sufficient, safe, and nutritious food that meet their dietary needs and food preferences for an active and healthy life. And this has been a very strong guiding principle for Mars when we operate day to day on quality and food safety. We see quality and food safety as synonymous aspects, and we take a lot of different measures to ensure that the foods we produce are safe, and we do consider that if it is not safe, it is not food. And that is definitely a guidance for us as we move today. But to think of where we are today and where we're going to move in the future, the challenge around quality and the challenge around food safety has never been greater. And a lot of points may have already been made by prior colleagues that have presented at this point, until this point. But to think about this as a global level, that if we predict that the global population is going to reach 9 billion by 2050, and maybe we will exceed 9 billion by that time, given where their current global population is, we need at least 50% more food. And to improve access to food, not just by increasing production, but by also decreasing waste, we need to solve multiple problems simultaneously. We not only need to double the food production, we also need to end hunger, and which means providing access to quality food across all levels of economic strata. And we need to do that while also drastically reducing the damage agriculture is causing to the environment. So, and this is, adapted from Scientific American. So, but this is the balance we need to attain. And we keep this in our mind as we look at how we solve the global food safety challenge, because food safety is indeed a global issue. And it is not restricted to one continent. It's not restricted to one country, even though there are specific figures here in millions of dollars worth of losses, so millions of cases of illnesses, loss of productivity. We still are working towards solving many of these challenges, but the situation is clearly serious. And unless we take a global step towards addressing food safety as a global issue, we're going to find more and more data like this in the future. And that is the situation we want to mitigate. So looking at the safety context, and some of this has also been highlighted in the plenary presentations in the earlier part of the day, that there are several factors affecting food security that include climate change, that include processes and the wastage we find during agricultural production and storage, and food manufacturing and consumer contact. There's various sub-processes within these large sets of large processes that affect food safety by contamination of raw materials, incidences of pathogens. And by mitigating these risks, by improving access, by improving availability, by improving utilization, we can create a situation where the food is more secure, which makes it more available, which allows us to manage the environmental footprint. It allows us to expand trade opportunities by lowering the food production costs. And we want to be in the situation. We want to be in a situation where many of these risks are mitigated to improve food safety. But to do that, what needs to change as a global mindset across manufacturing, across agriculture, across the food industry overall, is that we need active monitoring, which means we need quality processes that can determine hazards before they find their way to the consumer. And we need to do this in a systemic way. We don't want to be doing different processes in different places, but we want to take a common process as kind of a harmonized process, like Cesare was talking about. We want to talk about having a systemic way of identifying these patterns at a scale never done before, because that's what it takes to be able to globally help the food safety context, help improve food access. And we need to find a way of preempting the impact on consumers in a way that is scalable throughout the industry, in a way that we can create synergy or controls for prevention, not for post-incident management, but we need the active monitoring processes and the systemic ways of identifying these patterns in order that we can prevent incidences and improve food access. So we have several opportunities here that we can use to drive fundamental improvement. And some of these opportunities include using big data, using technologies such as sequencing to identify the microbiome, such as high throughput mass spectrometry to conduct metabolomics, and to use high throughput sequencing, next generation sequencing, taking the genomics approach. But by combining these approach technologies and the approaches they facilitate, how can we, given the known risks, as well as the unknown risks and the destabilizing effect they have, can we transform this capability globally? And if we can, how do we transform this globally? How can we solve this as a global problem? And in order to do that, what can we do with the emerging science, technology, and the new knowledge? And then we started asking ourselves, can we create a breakthrough in our food safety approach using genomics? The paradigm of culture-based testing is still widely prevalent in the food industry, as explained by Steve before. But once we get past that, by Francois before, I apologize. But once if we take a genomic-based approach, transform that approach, and if we think that to do that, we were to go and sequence the genomes of our supply chains. Can we understand the ecology? Do we have the tools necessary to do that? And if the tools are living up to the mark, can we understand the ecology? And I mean, what does it mean? And if we know what the ecology means to us, can we understand what it means when the ecology is changing? And if we understand how that ecology is changing, what then happens to that ecology when there are interactions at different stages of a product's life cycle? So what we thought was, well, if we enable the controls and efficiency for this if we create this food safety approach using genomics, we can enable controls and efficiency for our raw materials. But even more importantly, we can build a new approach to product safety from farm to fork or farm to plate whatever the right terminology is there. And initially we thought, what can we do with genomics? Can we do traceability? Yes, I mean, we can do traceability in different ways by using the outstanding power of the genomic data to attribute sources of issues. And those issues can be traced to a specific organism. They can be traced to the specific material. They can be specific to the supplier who's providing us the material, and it can also be specific to the supply chain itself. So traceability or fingerprinting is something genomics can enable. But what if we understand the interplay and the dependencies of microbial communities? What would that help us address from an industry perspective is to, just like Francois was describing earlier, the human body is not a sterile organism. It has its own microbiome. So would the food manufacturing environment have its own microbiome? And we can possibly define, using these approaches, what the factory microbiome is. And if we can define what the factory microbiome is, we can then ask the question, why do certain factories develop specific, what we call microbial residents? That you do the best cleaning you do, you go through your best sanitation procedures, but over time you continue to find the same serotype, you continue to find the same serovar, the same genome, the same microbial genomic variant over and over time. But then we would want to ask ourselves, why is this resident, and where is it, or is it really a resident, or is it a transient? And if it is a transient, then I go back to my previous question and ask, well, can we trace it if it is a transient? And again, that leads us back to the prior questions as to, is it specific to whom, specific to where, how? So, and by using these approaches, by applying genomics, we can develop new indicators. And this is a capability that the food industry has not experienced before, that we can look at everything in a single test. So, and of course, there are limitations here. I mean, depending on how deep you're able to sequence the metagenome or the microbiome, to what extent can you quantify everything in one go? But what we really want to see here is, yes, we are not looking at the absolute everything, but we have the opportunity here to broaden our perspective on what are all the indicators, and who are these indicators, and how are they indicating to us the interaction, the play they have between other members of the community and themselves. And which means that if there are going to be some that have this interplay, and they are going to be the ones that are of interest to us, because they may either aid or they may either deter the development of specific residents, or even facilitate the transience of certain microbes, for example. So, but again, if we take all of these aspects into account under the application of genomics, then we can provide the data to help drive the post-market surveillance, to say we are confident that our products in the market are safe from microbes. So, and in this point, what questions have we answered, and where are we? So we have answered several, what we would say, somewhat smaller questions as across the global context. That we say that, I mean, do we know that we can identify a biome? microbiome or the overall biome of a matrix? And the answer is yes, we can do that. And can we create a baseline? Yes, we can definitely create a baseline. Can we say who's there? I mean, what's the name of the present organism? The answer is yes. We know how to do that. And can we do this accurately? The answer is yes. So how did we get there? I mean, that's the key. That's a key piece of the puzzle. So this was the joint effort of a consortium that Mars and IBM developed along with jointly developed along with Bio-Rad that enabled us the identification of a matrix and enabled us to identify community diversity within the samples, and then allowed us to identify 60 hazardous genera known to be incident in microbes very accurately. And we could identify that there is a baseline variation from what would be considered normal. And based on these indicators, we were able to generate a general hazard index that allowed us to get closer to the stoplight scenario where we can interpret for the business whether it is a go or no go, or whether it is somewhere in between. So I would like to pause at this stage as the first part of my presentation and highlight the members of the Sequencing the Food Supply Chain Consortium that included Mars, IBM, UC Davis, Bio-Rad, and Cornell University, and with generous amounts of data previously generated through the 100K pathogen sequencing, pathogen genome sequencing project, and come back later for the second round of the conversation. Thank you.
Thank you. Thank you very much indeed, Bala. I think you both and you and Francois highlighted the importance of the microbiome, and I think there are numerous efforts now ongoing for the assessment, how the microbiome plays into food safety assessment. So I think it's quite important to consider that. Now we have one more speaker, and he is coming from the German government. And the German government has taken it upon himself to look also into the use of non-targeted methodologies. And they have a number of working groups. I'll introduce Dr. René Becker, who is the secretary of several of those working groups. And he is born and bred from Berlin, Germany. He, after graduating, he studied chemistry at the Humboldt University. And for his diploma, he joined a research group of applied analytics and environmental chemistry and focused on mass spectrometry-based quantification of proteins through metal labels. After graduation, he started at the Humboldt University for his doctorate. And for his thesis, he utilized quantitative proteomics to analyze predatory bacteria. And in 2018, he joined the German Federal Office of Consumer Protection and Food Safety, to many of us known as the BVL, where he's now responsible for several expert working groups of the official collection of methods. René, your turn. We cannot hear you right now, René, unless you're not speaking.
Can you hear me now?
Now we can, yeah.
Nice. Okay. Thank you for the kind introduction and also for the opportunity to give this talk. In my presentation, I will show you some of the activities in Germany regarding the validation of non-targeted methods in food analysis. But first, I would like to give you an introduction about the official food control in Germany and also about my work to give you some context. So As you might know, Germany is a federal republic consisting of 16 federal states. And according to the German constitution, the basic law, the official food control in Germany is executed by each federal state individually. Therefore, each of the 16 states has its own ministry responsible for the food control. The analysis of the food control samples is performed in 33 official food control laboratories. Therefore, the larger states, like for example Bavaria, have several official labs, whereas the smaller ones usually just have one official food control laboratory. Then on the federal or German government level, we have the institution where I work, which is the Federal Office of Consumer Protection and Food Safety, or in short, BVL. The main aim of this federal agency is to manage risks and also to communicate risks transparently. It has therefore several different tasks. Since the official food control in Germany is organized on the federal state level, our Department 1 at the BVL is responsible for the coordination of the official food control between the federal government and the federal states, as well as between Germany as a whole and other countries or the European Union. The Departments 2 and 4 are responsible for the approval of plant protection products and of veterinary drugs in Germany. And in Department 3, we have the authority for the approval of the release of genetically modified organisms for scientific trials. Last but not least, we have the Department 5, which is the department where I work. So Department 5 is the laboratory department of the BVL. Here, the European Union Reference Laboratory for Residues of Veterinary Drugs, as well as 8 national reference laboratories, are located. Moreover, the national monitoring of antibiotic resistances in domestic and food-producing animals is also located here. And finally, we have my unit, which is the Office of the German Official Collection of Methods of Analysis and Sampling. So what is this official method collection? According to paragraph 64 of the German Food and Feed Act, as well as to the German Tobacco Products Act and the German GMO Act, the BVL is responsible to provide a collection of standardized and validated methods to the food control laboratories of the federal states. The method validation for this collection is organized in working groups consisting of experts from official and private food control laboratories, as well as research institutes. Through providing this collection of validated methods to the official food control laboratories of the different federal states, the official collection is somewhat the foundation for the consistent nationwide quality of the official food control in Germany. So how is the method validation in the working groups organized? The process starts with an analytical method. Methods can be based on house methods or on publications or methods that are already in the collection and need to be updated. An important requirement for the selection of methods is that they have to be fully developed. So we don't do method development in the working groups, but only method validation. After the method is selected, it is then usually optimized and tested through pilot studies. And if these pilot studies are sufficient, then a method draft is created, and based on that method draft, an interlaboratory validation study is performed. And if the validation criteria are met, which is mainly the reproducibility standard deviation, then the method is finalized and published in the official collection. On the next slide, you can see all the currently active working groups for method validation at the BVL. In total, we have currently about 30 working groups. And as you can see, the oldest groups date back to the 1970s. So this official collection has been around for quite some time already. The older working groups, so from the 1970s, 80s, and also in part from the 90s, were mainly vertical groups, meaning that they focused on the method validation for a specific food matrix. Whereas in recent years, the focus of newly founded working groups shifted more towards horizontal groups, meaning that they focus on the validation of methods for a specific analyte or analytical technique and not for a specific matrix. In my talk regarding the validation of non-targeted methods, I will focus on the 6 highlighted working groups, so mainly molecular biological groups such as NGS, and also spectrometric groups such as NMR, mass spectrometric, protein analysis, and MALDI-TOF. But before I go into any details regarding the activities in the working groups, I would like to address a very central question regarding the applicability of non-targeted methods for the official food control. So the main question, and therefore also the main challenge, is how is the validity of the results ensured? Or in other words, if an official food control laboratory is performing a non-targeted analysis, and based on these results, it files a complaint, and this complaint goes into court, could the non-targeted method be attacked by the defendant? And if so, which parts of the methods could be targeted? So first of all, the sampling or the sample preparation could be targeted. For non-targeted methods, the sample and the sampling and the sample preparation are usually the same as for the targeted methods, therefore providing no specific challenge for the non-targeted methods. Therefore, this potential objection target could be dispelled by means of a classical interlaboratory validation. The second target could be the analytical measurement of the sample. For non-target methods, the analytical measurement is usually a bit more complex than for the targeted methods. General means to address this challenge could be a high degree of transparency regarding the measurement and the measurement parameters, and once again, of course, an interlaboratory validation of the measurement to prove the reproducibility. This interlaboratory validation should ideally include devices from several vendors. The last main target for objections could be the data analysis, consisting of both the reference database as well as the algorithm for the data analysis. For non-targeted methods, we generally need some kind of reference database to identify the detected compound. And in order to not make this reference database attackable, its entries have to be authentic. And lastly, we have the algorithm for the data analysis. Since the data obtained by the non-targeted method is usually too complex for manual analysis or for analysis with simple algorithms, we need to analyze the data with complex algorithms or even with artificial intelligence. And for this kind of challenge, there is no generally accepted solution to address this challenge. No generally accepted solution has been developed yet. But of course, there are several groups who, especially international groups, who are currently working on solving this challenge. So let's go into the activities of the BVL working groups regarding non-targeted analysis. So first of all, the molecular biological methods. For this talk, I will focus on barcoding and meta-barcoding. So what is DNA barcoding? So first you have a food sample from which the DNA is extracted. And subsequently, a specific DNA fragment is isolated, which is often a 16S rDNA fragment. And this isolated DNA fragment is then amplified by PCR and sequenced. The sequence, which is somewhat like a barcode, hence the name barcoding, is then compared to a database to identify the genus or the species. The workflow for the meta-barcoding is pretty similar to the barcoding, with the main difference being that not a specific DNA fragment is isolated, but several different DNA fragments are amplified in parallel. And this complex mixture of amplified DNA is then sequenced rapidly by next generation sequencing. The identification is then once again the same as for the barcoding. So let's apply our previously described challenges on these methods. For this analysis, I will focus on the meta-barcoding. It is nevertheless also applicable to the barcoding, although to a lesser extent. So as I said, the sampling and the sample preparation are basically the same as for the targeted methods, therefore providing no specific challenge for the validation of the non-targeted methods. Then we have the analytical measurement of the sample, which in this case is the sequencing by next generation sequencing. One potential challenge of this part of the workflow could be that there are several different device types that all fall under the general term of next generation sequencing. Therefore, several different device types should also be included into the validation, interlaboratory validation study, making the validation a bit more complex and expensive. And lastly, we have the data analysis consisting of both the reference database and the algorithm. For those molecular biological methods, the identification is usually based on public online databases. One big advantage of the identification for molecular biological methods is that it is mainly based on the sequence, which makes the reference database relatively simple. Therefore, even though the entries in the public online databases might not be the most authentic, they are easily verifiable by doing a sequencing of the selected species. And due to this simplicity, the algorithm for the data analysis is also rather simple. So to summarize, the main challenge for the validation of meta-barcoding would be the measurement of the sample, which is still not that hard to overcome. So for this reason, there has already been a high amount of activity in the BVL working groups regarding the validation of non-targeted methods. So on the next slide, you can see a selection of recent activities of the molecular biological groups. So in 2020, the working group Molecular Biological Methods for Plant and Animal Species Differentiation has published a barcoding method to identify mammals and poultry in food. The corresponding meta-barcoding method is currently validated by the working group NGS Species Identification. And moreover, the working group NGS Bacteria Characterization is currently validating a method for the whole genome sequencing for the typing and characterization of bacteria. So let's go to our next technique, NMR, or nucleomagnetic resonance spectrometry. The BVL working group NMR has very recently started a project to validate a method for the differentiation of honey varieties. So this is a method to verify the food authenticity in regards to the honey varieties. One remarkable feature of this method will be that it will use artificial intelligence for the data analysis, making it one of the first validated methods in official food control utilizing this technique. So once again, let's assess these methods to our challenges. So again, the sampling and the sample preparation are pretty straightforward and no specific challenge. Moreover, the analytical measurement of the sample is basically the same as for the targeted NMR, which leads us to the data analysis. First of all, the reference database. In order for the artificial intelligence to function and classify correctly, the samples for the training set really have to be authentic, making it one, if not the main challenge of the validation. The training set should also account for the variability within each honey variety. In order to reduce the complexity of the validation, the initial methods will be limited to differentiate only between 4 varieties. The honey samples for the training set will be collected over several years to account for seasonal variation. Apart from the NMR methods, the honey samples will also be analyzed by several other analytical methods to further verify their authenticity. Okay, let's go to the algorithm for the data analysis, or in this case, the artificial intelligence. For the artificial intelligence, it is very beneficial that the question the artificial intelligence has to solve is relatively simple. So it has only to differentiate between 4 varieties. And especially if you consider that there is no consent regarding the general approach for the validation of artificial intelligence in food analytical methods yet. And since the sample collection will take a few years, so the method validation will also take a few years, future possible legislation will have to be considered. So as you can see for this NMR methods, the effort to validate a non-targeted methods can be quite high. However, if the data obtained by the non-targeted analysis is not used as evidence in court, a complex validation of the method wouldn't be so mandatory, which leads us to screening methods. So basically, a food control laboratory could do or could perform a non-targeted analysis to identify suspects and then use validated targeted methods or even a site inspection for confirmation. And in this regard, we can see the activities of the working group MALDI-TOF. So this working group uses MALDI-TOF MS fingerprinting, meaning the shape and pattern of the spectra, to identify bacteria and other species. In this year, the working group has published a German guidance document for the single laboratory validation of MALDI-TOF MS fingerprinting methods, which also considered the newly revised standardization validation standard, ISO 16140. Apart from the targeted confirmation analysis, the guidance document also includes the single laboratory validation of non-targeted methods for screening. The last working group I'm going to talk about is the BVL working group mass spectrometric protein analysis. This working group focuses on the validation of methods for food allergen detection and for food authenticity. The main use of non-targeted analysis in this group is to identify potential marker peptides. So basically, you have a pure or authentic sample, and then the sample preparation is done, which means mainly the proteolysis, and the resulting peptides representing the whole genome of the sample is then analyzed by liquid chromatography, high-resolution mass spectrometry. And based on these results, the most distinguishable peptides are then identified and can then be used as marker peptides for a targeted multiple reaction monitoring or MRM method. And this MRM, targeted MRM method, is then validated by the working group in an interlaboratory validation study. So right now, the working group is not validating non-targeted methods, but only targeted methods. However, when in the future the high-resolution mass spectrometers become more widespread among food control laboratories, it is very likely that the validation of non-targeted methods, non-targeted proteomics methods, will also be approached. So in the last slides of my talk, I would like to point out that the BVL working groups are, of course, not the only groups active in the validation and especially the standardization of non-targeted methods. We also highly cooperate with the national and international standardization bodies. So namely the DIN for Germany, CEN for Europe, and of course ISO. In fact, the validated methods of the official collection are often transferred to the standardization bodies to become standards. And in the other direction, we also incorporate standards into our official collection. Regarding the validation of non-targeted methods, I wish to especially highlight the recently founded technical committee Food Authenticity by CEN. As you can see, several working groups have been founded under this TC that focus on the standardization of non-targeted methods. So for example, the working group NMR analysis, or more generally, the working group validation concepts of non-targeted methods. And of course, there are also the German mirror committees by the DIN that are also active in the field. And with that, I'm going to finish my presentation. Thank you.
Thank you very much, René. Very nice presentation and very good overview. I think it's fair to say that the BVL, the Federal Office for Consumer Protection and Food Safety, is a very strong contributor to the method collection that we have at the CEN, and often then also some cases go to ISO. Okay, now we're going to the second round of presentations, and I will continue with my part, and that will pick up on some of the items that Renee previously mentioned. So I'm going to share that screen with you, so I hope you can see that screen. Okay, here we go. 1 second. So let's talk about the message, and we're going to skip that slide here. So one of the challenges is that the importance of non-targeted method has increased, and many working groups have worked to develop such method because of their potential of being able to screen for so many different potential analytes, or in our case, adulterants. So the number of methods has really increased almost exponentially. I predicted fairly early on that in this year, so 2021, we will be seeing more than 2,000 papers, manuscripts published on either non-targeted or untargeted methods. So when I checked in September, mid-September, we were already fairly close, but not quite there yet. So I checked again yesterday, and we actually already in October exceeded the number of 2,000. So at this point in time, we have 2,003 manuscripts published that relate to either non-targeted or untargeted methodology. And for those of us working in a laboratory and having to select methods that we may wish to deploy, it is very challenging to identify among the 2,000 plus methods that have been published this year, let alone the year before and the year before. So right now we're looking at close to 13,000 manuscripts, the best method available for performing such screening tasks using non-targeted methodology. So where does it lead us? Usually the first stop is standardization, because a standardized method, it's been validated, it's gone through multi-lab validation, so the method is safe to use. The problem with validation is, the problem with standardization is that very often you have a large time gap between having a method submitted and then having the standard published. It's not rare that between the submission of a fully validated method to a standardization organization and the publication as a standard, several years pass. And we all know that science moves on, the fraudsters move on and become very innovative. So we need something that works a little faster than that. And this is where AOAC, one of the other standardization development organizations, standards development organization, SDOs, have really kind of made their mark, and this is using SMPR, standard method performance requirement. So basically, this is a situation where a community needs a specific analytical technology, so in this case, the non-targeted methods. And then there will be a description, there will be a working group put together. The working group will discuss what are, for example, the minimum performance requirements that makes a method fit for purpose for this task. And here we have formed a working group on food fraud methods, and there are two general groups, two horizontal groups. One is the targeted methodology group, and the other one, and that is basically breaking new grounds through AOAC, is the non-targeted methods working group. And here and I'll show you in a few slides down the road, we have the first set of SMPRs developed. So the working group on food fraud initially dealt with protocols for milk, for targeted and non-targeted, for honey, for targeted and non-targeted, and for olive oil, that you guessed, for targeted and non-targeted. So there initially we just considered the chemistry methods, but we very quickly realized that was basically falling short because we had completely ignored the molecular biological method that Francois and Bala mentioned, for example, the next generation sequencing, either whole generation sequencing or semi-targeted next generation sequencing. And we also expanded the group of matrices. So the honey, milk, and extra virgin olive oil were done, but we also now have included spices, which is in the food industry a particular challenge because they're known to be frequently adulterated, and botanicals. And now we have basically the verticals and the horizontals. So we have the different matrix groups, honey, milk, extra virgin olive oil, and spices. And we do have the different technologies. So we have the food chemistry techniques, targeted, non-targeted, and the molecular biology techniques, targeted and non-targeted. Now, as a consequence of that, a number of protocols or guidance documents, SMPRs, have been developed, and this is the one for milk, the non-targeted one. They're all published, they're all publicly available. And here is described what are the minimum performance requirements are that a method needs to fulfill in order to be useful as a non-targeted method for detection of certain milk adulterants. Now, Renee mentioned the newly formed TC460, that's the CEN, the European Standardization Group for Food Authenticity Method. And we have a number of working groups in that kind of technical committee. And now there are more than you see here. We have 8 by now. But one of them is actually the working group 5, and that's the second from the bottom that you see, that the working group on non-targeted method. So also you can see that those methods have become so important that even standardization is dealing with that. And recently I learned that now several laboratories in Germany have been accredited for example, metabarcoding, one of the other non-targeted technologies. And of course, there is also not just a liaison to the national bodies, so the DIN and AFNOR and ENOR in Spain, but there's also liaison with the ISO committees. So for example, the identification for animal speciation, which is a working group 2 of the CEN TC460, has a liaison with the ISO TC34 SC16 working group 8. And the NMR analysis on that, the working group 4, has a liaison with the working group 24 of the TC34. So we can see that's all pretty much intertwined. All the major standardization or standard development organizations have now included non-targeted methodologies into their sections, into their standards, and into their working groups, which also demonstrate the importance of these types of methods to help us with identifying challenges either on food safety side or on the food authenticity side. So it's quite important that we're making that step and that progress. But where are those targeted or non-targeted methodologies useful or the most useful? I think it's when we're talking about food manufacturer, in the food manufacturing process, they're probably not the most useful simply because you should know what you're using. But I think where they are very useful is when you need to screen for potential issues with incoming raw materials. And here, currently, we have a situation where randomly samples are being taken from incoming raw materials. They're being sent to the laboratory for analysis of potential suspected adulterants, or the high-risk adulterants, but you can never capture all the potential adulterants or issues or safety challenges that might be present. So this is where the non-targeted methodologies come very handy, especially if you could basically do a pre-screening locally. And I think that is the primary use where the non-targeted methodologies are extremely useful, and we've seen a number of applications already, and we know that many companies use, for example, NIR or FTIR for screening incoming raw materials. Already they have their databases built, so the use of non-targeted methodologies is not that new, but it's the widespread that is new. And we see also now a number of portable inline or at-line technologies that allow the simple screening by the push of a button. And here what we see, and that is quite significant, is basically the shift of the first line of defense away from the food laboratory, food testing laboratory, to the manufacturer's side. Because what you can do here is really a screening before you send sample to the laboratory for confirmatory testing that there is something going wrong with the sample. So maybe a presence of a pathogen or the presence of an adulterant. And I think that will not only save time, but also cost. And it will put pressure on the suppliers to ensure that you are delivered the highest quality of products. So I think here those devices and tools that are being deployed at the factory site for the screening of incoming raw materials will play a very important role in the future, but they could also be deployed, and Renee was talking about the enforcement side, could be employed or deployed by inspectors in the field. So imagine you get 1,000 bags of milk powder. How would you sample to check if the milk powder is okay? You can randomly sample, and you have a certain probability that you might hit the one bag that may have an adulterant in. Or you could use a portable technology, one of those what we call point and shoot devices, that simply look at, using NIR or FTIR technologies, look at what wavelengths are coming back, what certain elements might be in your product, and then identify if a sample is out of spec. And here we've seen very recently dramatic development of those devices, and I will just show you some of those. So when we saw there was a dramatic increase in portable testing technology devices, portable in the terms of you don't need a scientist, you do not have to have a PhD to interpret the results. They're basically simple devices that can be used that can be used on site by staff. So Carmen Diaz-Amigo and myself put a special section together, and you can, if you scan the QR code, you can actually get to that special section. And I will give you some examples of what these portable devices are capable of. And they're all coming from the manuscripts that have been submitted. That was last year, 2020, to the special section on portable devices. So here we talk about first the NIR, the infrared, and there have been two manuscripts. One looks at the freshness of fruits. So when you receive goods in the supermarket, the employees of the supermarket could simply test at the push of a button if the grapes that you have just received are fresh or not. And the device will give you an indication. And if they're not fresh, you may reject that. Or if the fish that you're receiving has been farmed or has been caught wild and may just be, mislabeled as wild if it was farmed. So here, simple technology, simple push of the button technologies that come with a fairly high intrinsic complexity can be used on site in supermarkets at food manufacturing sites. Similarly, here you have a case of rice, and we all know that, for example, the basmati rice is very highly appreciated also in Europe, and there's even a lower levy on true basmati or authentic basmati rice. But very often you have shebuti or other rice varieties intermingled, and it's not a pure basmati. And again, NIR can help you very quickly and at the push of a button distinguish and discern between an authentic basmati rice and something that is commingled. Here we have trans fat analysis. There are certain regulations around. In Europe, we have 2019 649 on how much trans fat you can have in a product. And again, this is a tabletop small instrument that allows you to quickly measure and determine how much trans fat is in the product. Again, you don't need to be a scientist, you don't need to have a PhD. It's a simple device, push of a button, you get an answer. And the last example that I would like to share with you is, and I mentioned the extra virgin olive oil at the beginning, and this is basically a triple sensor. So it has 3 sensors built in. One is a fluorescent sensor, one is an NIR sensor, and the third one is a visual sensor. And it basically allows you to discern if the extra virgin olive oil is authentic, or if there is a intermingling with refined oils, with olive pomace oils, and with other oils. So it's really a very simple tool, again, point and shoot device that will allow you to determine at the push of a button and within seconds, without having to send a sample to the laboratory, the authenticity of the olive oil, the extra virgin olive oil. So here, I think we've seen one of the most useful uses of non-targeted technologies, that is the on-site use for screening. And then once you have identified a sample that is out of spectrum, out of spec, you can send it to the laboratory for confirmatory testing. And with that, and the unusual peak that you see here, I will finish my part of the second part of this presentation. So thank you very much. Now I'm going to stop sharing the screen. And I will hand over the next in line. I believe that was, give it Steve Holroyd with the second part of his presentation.
Afternoon again, everyone. Welcome back to the our second session. Just confirm they can see and hear me. All good there, Bert?
Yes, we're good. I can hear you and see the slide in presentation mode.
That's great, thank you. I'll just, so thanks again for your attention. So previously I talked about the example of using mid-infrared spectroscopy as a method, as a non-targeted method to detect potential adulteration. Now I'm going to talk in more detail about the standardization of non-target methods for food ingredients. This highlights work that we did in conjunction with US Pharmacopoeia. I led a project on the guidance in developing and validating non-targeted methods for adulteration detection. So here we were developing a guidance that could be applied across a wide range of analytical methods to develop non-targeted methods. And I'd like to talk through the steps we took, many of which the other speakers have highlighted in specific cases. And obviously also this is, I guess, a US Pharma colleagues who we worked with and couldn't have done this work without. A number of people from USP and also a number of people from different organizations around the world who contributed a lot to the development of this, this guidance. I'll also just mention as a way of background to the US Pharmacopoeia, they published the Food Chemical Codex that many of you will be aware of, independent standards developed with volunteer experts, about 1,200 monographs in there, and they define a lot of what it means to be food grade, methods to determine whether an ingredient sample meets the standard. They're regularly updated and revised, and they contain both monographs, so definitions of what a foodstuff is, in this case perhaps krill oil, and then an outline of general tests as well. And this example is our guidance on developing and validating non-targeted methods for the detection of adulteration. We know about food fraud and we've heard about it. I won't dwell on this too much, but it's a misrepresentation of the true identity or contents of a food ingredient for economic gain. Things can be adulterated. It can be very hard to detect without some sort of sophisticated analytical testing. We know food fraud is quite prevalent as well, up to 10% by the UK Food Safety Authority suggested. Detection can be typically quite low, and it's been going on for a long time in the food business. And we've heard reference to this as well, the challenge of detecting for food fraud. We can develop a targeted analysis, which looks at a specific marker or adulterant. Criminals who are engaged in adulterating food systems can respond to that. So we can go back and forth. And this is really the genesis of non-targeted methods. We've seen this slide a number of times. It's a great slide that shows very clearly the difference between targeted analyses and non-targeted analyses. But it's not easy doing this. Once again, as we've heard, a lot of companies have the infrastructure. We do a lot of testing in the food industry, but sometimes this jump between quantitative analytical tests and qualitative or non-targeted tests is quite challenging. So lack of information about the generation and application of non-targeted methods, lack of standardization. What does it mean? How do you validate it? We've touched on a number of these challenges here. And organizations can really have a number of challenges of understanding the risk tolerance and how you actually gain a representative view of your calibration model. What are the essential elements of a non-targeted method? Because you need to think about this if you're doing your guidance. You have a sample, and you have some sort of analytical procedure, and you have a reference set, a set of products that are known to be good. All sorts of examples for the analytical procedure, spectral, chemical, or wet chemistry. You do some sort of testing, you have an output from that. It can be spectra, chromatograms, images, multispectral images. And then using that output, you do some sort of statistical testing, what we could call here a similarity assessment procedure, and you get some sort of significance level. And you're trying to decide with that sample you've measured, the single sample you've measured, is typical or atypical with reference to the wider reference sample set that represents typical samples. So a binary decision is reached. This is the study that sparked US Pharmacopoeia's interest in this. We were looking into a number of years ago, melamine in skim milk powder. Melamine is one of the original adulterants, but something that's been very high profile, is often used as an example. If you're looking at skim milk powder and you're using near-infrared spectroscopy, you can get a trace in this wavelength range. Not adulterated, you can see there's no peak. If you add melamine into that skim milk powder and dry blend it, mix it up in a dry state, you get a peak due to actually the melamine molecule that's present. However, if you wet blend it in, you add the melamine into liquid milk, and then you make skim milk powder, you dry it to skim milk powder, you don't actually see that. And this was rather a strange result. And we wanted to explain, in this context of working with US Pharmacopoeia, we wanted to explain how that could happen and understand how non-targeted methods could be used to detect these sort of changes. To talk a little bit more about the dry and wet blending difference, dry blending is when you're putting two powders together. Wet blending is when you put, it may be more common in some adulteration situations, certainly it is in milk. It's quite hard to dry blend on a large scale, especially if you're perhaps a criminal with an intent on adulteration. Hard to have a large scale manufacturing facility, whereas wet blending in milk case can be more easily done with an adulterant. And there's a physical difference around the samples. We've got here polarized light microscopy. The melamine you can see on the top left, it's quite distinctive. Skim milk powder is also distinctive and very different. If you dry blend the two together, you can see on the bottom left, there's elements of melamine crystals in that dry blend. When you wet blend it, you don't see those. The melamine is much more finely distributed. So it's actually a different analytical challenge. How do you detect that versus the dry blending? Ideally, you need to be able to do both. But using that NIR approach, NIR testing approach, you saw one and you didn't see the other. So how do we actually then develop a non-targeted test that takes this difference into account? This is a further advance on the work. We developed did near-infrared spectroscopy, in this case, a SIMCA test, a statistical test, and the red samples of the calibration reference set. And we found as we actually added more wet blended melamine, you could actually see it, but you needed to understand the concentration and the dose response level. So you build a model, and this comes back to careful validation. My colleagues have also mentioned, you carefully validate it with both dry and wet blended samples and understand its performance against both as part of the validation process. We show that from this, the non-targeted methods are beneficial, even when you know what the adulterant you're looking for is. And for reference materials that are genuinely fake, you need some sort of standard. And US Pharmacopoeia actually put a lot of work into this and actually prepared deliberately adulterated skim milk powder with a melamine at a certain level that you can buy as a standard that's wet blended in. So that's kind of representative. It's like a genuine fake you can use as a validation protocol, as part of your validation protocols. And we've heard market trends around this. There's many vendors and using selling non-targeted methods. They're often used as screening methods, followed by more targeted methods for abnormal samples. And there's a lot of investment both by companies like ourselves at Fonterra, contract testing labs, as we've heard, and also regulatory authorities as well. So lots of activity, and we've had representatives of these organisations as part of the panel today. So we've developed our non-targeted guidance for adulteration detection. It wasn't a straightforward process as developing standards often is. Started in 2015, started with the team I've mentioned earlier in a draft, and went through the process, the US Pharmacopoeia process, developing and finalising and publishing that standard, which was published just going up to 3 years ago. There's some definitions, and it's really important. In the literature, people have written about non-targeted methods. Bert showed the plot of literature that's just boomed around non-targeted or untargeted methods in scientific literature. It's really important in a standard to define aspects of how the standard works. And I mentioned these terms of sensitivity and specificity in my previous talk. This is how they're defined in the standard, and we're trying to make sure that there's a shared understanding of such definitions across the area, because it's really important if you're going to understand and validate these non-targeted methods that you have a unified and uniform approach. And we're hoping other standards development organisations align to this as well as work goes on. The logic flow of the US Pharmacopoeia's non-targeted guidance document, it's got an applicability statement. As I said, it's meant to be generally applied to any sort of analytical technique, or not any, the ones that generate a wealth of chemical information. There's quite a lot of them. You do method development using a reference set, you define what's good. We give guidance around how you might do that. We apply the test set to the method and understand what the variation looks like. Evaluate it and do feedback, so that once you've evaluated the method, you look back at the applicability statement. Is it still working? And go through the cycle again. And then interpret the results and monitor and maintain the method. The guidance document lays out how this is done in a generic fashion for non-targeted methods. In conjunction with this work and my other colleagues, the US Pharmacopoeia has published a number of examples of applications of non-targeted methods in a range of matrices using different analytical techniques to give good examples of how you develop and deploy non-targeted methods and some of the challenges around it. Some of these papers had lots of authors because it actually is truly quite a multidisciplinary approach developing these methods. To conclude, there's many analytical techniques which can be rapid and expensive. They're really good for applications for non-targeted testing for both known and unknown adulterants. Combined with targeted methods, you have this hierarchy of testing many of us have mentioned, and USP has been as a key player in this, addressing this gap around the standardization for use of non-targeted testing. Thanks again for your attention, and Bert, back to you.
Thank you very much, Steve. I think it's also worth mentioning that the food fraud database was originally implemented by USB, the United Standard Pharmacopoeia, and that has now been sold on to Discernis. And I think several of us still use that database as a resource for the number of adulterants present. So thanks again, Steve. We're now moving on to François, second half of his presentation.
Yeah. Thank you, Bert. Here I am. Presentation. So maybe I spend too much time in the Pasteur Institute. That's the fact, being French, but sometimes I like to be old-fashioned and go back to the roots of the techniques. When we speak about NGS, there is a next, which means that before NGS, we had generation sequencing, and generation sequencing was based on the Sanger technique, which was capillary electrophoresis with very short read. So maybe some of you are wondering what's on the left. This is an image of the type of gel we were having, the very long acrylamide gels, very troublesome to perform, very long, a very short read, which means that 20 years ago, when you want to sequence a global genome of just a single microorganism, this was, for example, for Listeria monocytogenes, a European project, a science publication, 50 scientists just for one genome. Nowadays, sequencing a genome of Listeria monocytogenes, this is done within a week with a robot, and you wouldn't get a science paper if you publish a sequence of a genome of Listeria nowadays. Which means that NGS, this next generation sequencing, is massively parallel sequencing technique, which is considered to be the second, and we also speak of sometimes of third generation sequencing. And HGS is really a catch-all term, which is used to describe a different number of modern sequencing techniques. It's not one technique per se, it's the set of techniques to explain how fast and accurate the sequencing now can be done. And even Bert was mentioning with a handheld device, right now with your iPhone and Oxford Nanopore, you can sequence a Listeria genome. So we've got, within NGS, we already go from NGS 1.0 to NGS 3.40. The first revolution was with the whole genome shotgun. Second was with the high throughput sequencing, thanks to the tools, the robotization, you could go make it faster. And now with the third revolution, it's going down to single molecule sequencing. You don't need so much sample to do so. So this is really, really helping a lot and providing a lot of information, but maybe too many, which means also we need to understand with all this set of information that we are gaining from NGS, okay, what does make sense, what does not make sense, what can I use? We have a regulation in Europe, the 178/2002, which is the mother regulations for food law, who say that it's the responsibility of the food business operator to ensure safe food, which means if you make the sequencing on your food products and you have that information, you have to deal with it, which means that you need some annotation, some understanding of all the massive information you are getting from this sequence. That's something that we discussed and published in IGFM following the IAFP Europe conference in Athens in 2015, that in fact with the microbial risk assessment, we need to integrate meta-omics. So there is a next level of integration to consider within the microbial risk assessment. It's far more than just one pathogen and what do we do with it. It's a pathogen in a food matrix, in an environment, and different condition, and interacting with the common soil flora, interacting with the food matrix. So it's when you believe that we've done it all with microbiology, guess what? No, we are far from there. It's still a very young science. When you think about it, we're just less than 150 years old. We still have the chance and opportunity to be discussing with grounding father of new techniques. So there is a lot to learn. When it goes to microbial mapping with NGS, there are a lot of potential application that you can have. I'm taking here two examples, one from Italy and one from Ireland. With the coexistence, for example, of lactic acid bacteria and potential storage microbiota in the dairy processing environment, this is something that we've been wondering for many years. And right now there is a huge focus, at least in Europe and in the US, but I believe also in ASPAC and in China, on processing environment monitoring. Why are there some resident strain? Why do some strain persist and why other just pass by? What's the interaction with the other microorganisms? Are biofilms single organisms or just another microbiota to consider as well? And the point is, could we use the microbiology of the processing environment to tackle this issue rather than to always try to get a sterile environment, which is not possible? Could we work positively with food cultures, with dedicated microorganisms in order to have a safe microbiota of the dairy processing environment? This is something also that the Irish, the CIFSQ, has been working on it with the environmental microbiome mapping in order to improve quality and safety in the food industry. You need to understand globally the impact of the processing environment for your food products. This is something, for example, in China to consider with your vinegar. In some province, you've got IGP protection from your vinegar, but this is not done on industrial scale. This is a household. This is a very low level. And when you try to develop this as an industrial scale, you don't end up with the same product, which means that there is more than meets the eye to scale up the process. And certainly the global environment of the factory plays a role in the final product. So I gave you this example on vinegar in China. We've got a similar example, for example, in France with Roquefort blue cheese, which I know is very smelly, but also we have very limited dairy processing sites for Roquefort, very historical wine, for a simple reason. We don't manage to process Roquefort in modern factories, because Roquefort is not only milk and the starters you inoculate, it's also the environment where the fromage, where the cheese stays for a long period of time. So we need to understand this in order to make sure that we have safe and quality products. So safety is something with NGS that is helping, but it's not full revolution. But with quality, definitely understanding the spoilage potential of the local microbiota and how to tackle this, we have huge implication behind. 16 RNA sequencing and metagenomic is also a global strategy that you can use for your environment. So environment samples who contains multiple organisms. So this is something that we published recently in IGFM. As mentioned previously by Bert, there was a dedicated expert group from ILSI Europe about this. This is an open access publication. This is a chapter 7, which was mostly written by Seamus Fenning from Dublin University, and that's why she wants to promote precision food safety, is really having a look on your microbial communities, using a specific data sets, really having a look on the taxonomy, what's present, going more than just the identification, like I've got Listeria there, I've got a Chronobacter, I've got a Salmonella, but what are the capacity of this microorganism? How can I explain why this Listeria is resistance and can stay there? And that's this data that the Irish have generated, who've shown that, that there is a lot of isolates from the environment which have benzalkonium tolerance genes. And the massive use of quaternary ammonium compounds in the food industry also explain why there is a selection on Listeria monocytogenes resident strains which are naturally resistant to these reagents. So that would be a way, for example, to understand the rotation of cleaning agents. Maybe when I don't clean, I have an issue. Where I clean, I set up, in fact, another issue. I am selecting resistant strain, which means that the rotation of the cleaning agent is necessary at some points in order to make sure that I can get away from arborigenesis in the environment with resident microorganisms. In terms of preventive action with processing environment monitoring, what's important is first the identification of isolates. I mean, know your enemy, know very fast what they are. For many years, we've been using basically phenotypic identification techniques like API gallery, for example. But we've seen in complex facilities that sometimes with just the phenotypic identification, you discover that you have isolates of Listeria monocytogenes. And when you go further in the typing, you discover that in fact, you've got 3 different strains on Listeria monocytogenes, which give you clear explanation on the route of contamination between the different workshop in the food processing environment, and will help you have better preventive and corrective action in place. The characterization as well is very helpful, because there is more information than the name of the microorganisms. From the sequence, you get a lot of explanation. For many years, we wanted to understand resident versus transient, and now we get a set. Some have better adherence properties, some have resistance to cleaning agents, some have operant genes or protective enzymes in order to survive in this environment. So the genetic information gives you a clue of the adaptation to the niche, the survival factor, and therefore it can help you having better mitigation in place, define better appropriate control measures, and make sure that what you do in terms of prevention will indeed be effective in order to tackle the contamination. It's also important to identify the microbial ecology of the food production. There can be some changes over the time. If you, for example, in the cheese, in the ripening, if you see some shift in your food products in terms of sensorial properties, and you didn't change the starter, and it looks all fine with the milk specification, maybe something's going on in your environment, and that's something where you need to have a look for this. And that's this new shift from classical food safety to precision food safety to get better information to tackle this is something very important in the next steps. We have a major trend going on in France, at least following our crisis with Salmonella agona in 2017, where right now there is really a focus on the corrective and preventive actions which are done, and making sure that we have indeed the best techniques in order to ensure safe production. So when it comes to these points, it's always asking, you will see a lot of publication mentioning that the NGS is a game changer. And indeed, NGS with the omics tools and particularly WGS for genome sequencing should be a game changer. For the authorities, they are already, because it helps detect more and more smaller foodborne disease outbreaks, or also outbreaks that last for many years. We've got this example with a salmon producer in Estonia, which were compliant with the regulation in terms of testing on the finished product testing. But in the Scandinavian countries, they've seen different isolates of Listeria which were of the same sequence, and it took them 5 years to understand these very small processing sites where in fact the environment was not under control. And without WGS, they would never have found it, and this could have lasted for many years. For the industry, it's important to have the identification of the pathogen of concern and the microbial persistence for the improved characterization of your isolates. And it's also very important for QA, for fraud detection. For example, when you've got specific products where you know that you can have specific fingerprints of their microbiota, it's very interesting in order to detect if it's really your food product or it's another one, because physical chemistry properties can be mimicked. Mimicking a microbiota, that's by far more complicated. Maybe it will come at some point, but for the time being, these are types of techniques that we do not have. So knowing precisely the microbiota of your food products, not necessarily pathogens, but as well the common soil, the starters, it's very interesting. If you have a proprietary strain that you want to use and you've got a competitor who's using the same type of species, but in fact he's using your strain, that's pretty interesting as well, because there is a trademark behind this. So there are lots of implications that these new techniques are offering. And with it, I conclude my talk. That was done on behalf of Università Cattolica del Sacro Cuore, the Dipartimento di Scienze e Tecnologie Alimentari. You see on the right side the boss, Lorenzo Morelli, on the left side the joker, myself, and the two ladies who indeed do the job, Vania and Alessandra. So you can see that since Robert Koch, Pasteur, and Julius Pretris, nothing has changed. It's still women who do the job in microbiology. Thank you, Bert.
Thank you very much, François. Very nice talk. And I think it's important to highlight what next generation sequencing can actually offer in terms of bringing food safety to a higher level, to the next level, indeed. So with that, I would like to move on to the second part of the presentation of Cesare Varallo.
Yep, here I am. Hello, Bert.
Okay, Cesare.
Yeah. I'll share the screen. Here we are. Okay. Current slide. Okay. I start from where we left, but I'll skip briefly. Those couple of slides are about the lab organization in EU. They were just to remark that we have a joint research center of the European Commission that has been set up for to manage a lot of, let's say, scientific activities, and as a knowledge center for the European Commission, but is also the European reference lab for certain areas like food contact material, additives, and GMOs, and establish and try to establish as much as possible reference methods, reference materials, and organize proficiency testing schemes for the laboratories in in the member states of the European Union that, as already mentioned, have a system of public labs, usually with central laboratories that perform high-level activities, and then local laboratories in different regions and municipalities, and one accreditation body, for instance, Accredia in Italy, that accredited those labs. But since we are discussing quite well also in chat about targeted and non-targeted methods, I would like to just give you some inputs about 2 or 3 examples where we can see the pro and cons of those non-targeted methods. For instance, when it comes to food fraud prevention and authenticity, I don't see much in terms of targeted and accredited methods that can be used, especially if you don't know what you're looking for, or you're looking for the origin of certain food, might be oil, vinegar, whatever. And so non-targeted is a must when it comes to prevention. So as Bala mentioned as well, the preventive approach is very important, and non-targeted methods will play a very important role in prevention of issues for the companies in the future, I guess, because with non-targeted methods, you can, of course, notice things that cannot be noticed with the traditional testing, the targeted methods. But when it comes to food fraud, you have for sure a lot of challenges, because the first one is the one related to reference materials, as already mentioned several times, because an apple is just not an apple. There are, I have no idea how many species of apples there are around the globe, probably, I don't know, 200, 300 botanical species. So when you have to establish what is authentic, what shall be used as a reference material, is always challenging. Then there are challenges related to the analytical method itself, about how it works, and the reproducibility of the results on different matrices or different samples, because the apple might not just be, you know, green, red, or of a different species, but might change also in composition from one season to another because of the weather and external factors. So those, to me, are the main problems when it comes to accreditation for non-targeted methods in food authenticity. And they cannot easily be overcome, I think, with the actual system of accreditation. I guess that I'm not a scientist, but I guess that the best way to move forward would be to establish a specific pattern to accredit those methods that might be a bit different, let's say more flexible, or adopt different criteria to establish if a non-targeted method is reliable or not, because clearly it's an entirely different story. But especially in Europe, we have another emerging topic that is very interesting and might work well as an example, the topic about dual quality food. So what's dual quality? Is a problem, according to the Commission, that can be described as follows. Okay, the manufacturers produce a very well-known food, a very well-known item that is recognized by consumers across all Europe, and for having certain characteristics, but in reality, it's different from one country to another. And those differences might be justified by, of course, a different local taste, different economies, so different prices that impose to do different formulations to stay on the market. It might be imposed by different legislations in the member state of the European Union. So to accommodate also local rules, you might have to adapt your recipe. And in those cases, according to the Commission, let's say that very generally speaking, you know, your difference in quality, you know, of the same product under the same brand, sold in the same package across the member states would be justified. But if you are just, you know, changing the recipe to brutally save money and create, let's say, some markets where you have a product that is of lower quality, you might be challenged by the authorities. under some general principle about unfair information to consumers. Okay, I will cut short on this because it's more labeling, but just to give you the idea, the problem here is how to prove that not only the manufacturer did this dual quality, this dual standard with the intention to save money, to cheat the consumer, that it's per se already a problem from a lawyer perspective, because prove the intent is never simple, but you have also prove that those two foods are not just different in composition or nutrition values, because this is not always defining which of the two versions is superior in terms of quality. We have no definition of quality, but you have also to prove with, for instance, organoleptic testing that the food is different. What the JRC is doing now is trying to establish a method to distinguish these dual quality cases. And this method is based on guidance about the evaluation of the label, the front of pack, and is trying to mix some traditional testing with also non-traditional testing like organoleptic test, blind test from consumers. We don't know exactly how this will be shaped in future, because it will be up to all the member states then to adapt to the JRC guidance. But you see that also in these cases, how you can standardize and accredit a method that is based on a blind test by a panel, okay, it's very, very tough. So in this case, for instance, will be, in my opinion, very difficult for the national competent authority to start any prosecution without a hard proof, an analytical proof, a report that established that one food is different from another. And as mentioned, it's not enough to say, oh, you have a different recipe or you have different nutrition values, because I saw a case about a cheese a couple of years ago where the German recipe was, from a nutritional perspective, much worse than the recipe used in the Eastern countries in Europe, because there were so much more fats, for instance, inside. But at the end of the day, probably the product might be considered better because there was real milk, real butter inside instead of dairy products that were not of the same value on the market, both from an economic perspective and from a nutritional perspective. So it's not so easy to define when you have a dual quality. This will be another area where the Commission is doing a lot of efforts, but to me, we will see many problems in courts when we'll come to demonstrate that something is different. The last case, it's coming from as an inspiration from Italy, from my country, because we had a brilliant idea around 20, 30 years ago, but we did an horrible execution as often. So we decided when you deliver feed to a client, usually feed is delivered in big consignments, you have to take samples in presence of both parts, seal them and preserve them in case of any controversy about the quality of the feed, okay? But we never define how to do those sampling. So exactly as René said, anytime we have an issue with the quality of the feed, we finish in courts and the parts discuss forever about how the sampling has been done, by who, with which containers, with which instruments, or in which part of these big consignments, if it was representative of not of the whole batch. So the aim was to prevent litigation, and the idea was correct, but the lack of technical rules and of an harmonized standard to do this, that clearly might not be always easy as doing sampling in a different environment, because you are basically discharging those huge consignments from a ship, from trucks. So you're not in a lab doing everything with instruments and all precise. Basically made this institute useless, or is creating probably more litigation than what is solving, because everybody take the samples, but they are just to challenge those samples in future, basically. So good idea, but it's not working. Why? Because we didn't agree on how to do this sampling, and the testing as well, but the testing might be done with targeted and standardized method. The big problem here is the sampling that, of course, is did in uncertain condition. So when you have to limit your liability as a company today, and you want to adopt as a standard methods the non-targeted methods, I would say that a good idea could be to agree with your clients, with your counterparts, about which kind of testing you do to accept raw materials, to accept feed, to accept incoming goods, and how to regulate the non-compliance. Because if you go in courts and you're adopting non-targeted methods, it will be hard for you to demonstrate that you are right and your client is wrong, and they deliver, food that is. This will be challenged for sure by the lawyers of your client, of your counterpart, and so the best solution at the moment is, if you adopt non-targeted methods, is to establish by contract which kind of methods you are using and what will happen in case of non-compliance. Because with a contract, of course, in courts you will have more contractual power. You can say, okay, but the other part voluntarily binded to use this method and consider this method as valid. So why now is saying that this method is not reliable, is not accredited? It doesn't matter. So that's at the moment, from my view, the situation from a legal perspective. And the challenges are clear. They emerge from any presentation, okay? To be established a standard ordinary test, they shall seek for some sort of accreditation, because at that point they can be used also in courts. Accreditation is not a simple goal for all the reasons that we mentioned, and without accreditation today, the non-targeted methods have a limited legal recognition, legal value attributed by the public system. A bit of legal value can be given to those methods under the free will of the parts signing a contract or an arbitration clause or whatever. So this might be the best advice for the present. We will see in future what will happen. Thank you, Bert. Close here.
Well, thank you, Cesare. I think the point is that we're now moving towards accreditation, but it will still be a challenge, because by definition, if it's a non-targeted method and you detect something that wasn't previously there, it might, but we'll talk about that in the discussion round later on. We still have one more talk to go. That's the second half of Bala's presentation. So I'm now handing over to Bala before we go into the discussion round.
Thank you, Bert. And what a great series of talks and discussions to follow through at this time. So we will continue to discuss further the development of this. So one of the curiosities in the audience might be that why so many big organizations come together to look at this challenge of supplying the food, sequencing the food supply chain. And the answer to that is that because of the scale of the challenge, because we heard all the previous presenters mention about the challenge of a non-targeting approach and how can it be usefully validated. But in order to do that, we have to have very highly curated, very high quality databases. We have to have very high performing algorithms and infrastructure that can deliver the results within a reasonable turnaround time. And we have to determine to what extent do we have to actually sequence. So if you take microbial isolates as for example, and if you don't have the right sequencing quality, and if you don't have, if you sequence very little of it, the confidence that you can place in your source tracking identification, it may point to that everything is looking alike, but that may be because more due to the poor data quality, and you might get a completely different answer had you sequenced deeper. So in order for understanding that, and particularly related to the food authentication strategy, that we were building together, it was imperative to think that we take the right approaches to the right data sets in order that we assign reads, we assign the raw sequencing reads that we apply for, that we obtain from the sequencer, and we are able to ascertain that given against a benchmark against multiple benchmark data sets, that we are able to within margins of error able to identify composition. And the published version of the study that I'm going to talk about carries the information around that benchmark, around multiple benchmark data sets, that shows that even with a non-targeted sequencing, DNA sequencing approach or RNA sequencing approach, we can very reasonably identify composition with very minimal error and with very high accuracy and with very good reliability. So we're going to show some data further down. I just want to make note that this wasn't a one experiment and done thing. It was a process that took several years to build the right quality of databases, to have the right perspectives, to have the right data collection. So the other thing is also that this wasn't a bioinformatic pipeline building effort. This was an end-to-end validation study that also generated operating protocols for specific food matrices. So the prototype for the microbiome analysis is called Kiwi, with several data transformation steps. But we want to highlight what this really does. So what this really does is you have two components of it, and I will actually be talking more about the second component today, that there is a matrix filtering aspect prior to identifying the microbial hazards, but there is a separate aspect that the post-QC does matrix quantification and identification. And these were done distinctly. I mean, could we have used the information from the overall matrix presentation of matrix filtering? There was a possibility for that. And we have to say that between the two approaches for matrix filtering and matrix versus identification, the results were fairly close, but the matrix quantification and identification pipeline that's listed, that's highlighted in the lower part of the diagram, gave very much more accurate picture of the percentages of various matrix components. So that was ultimately chosen as the key pipeline for identifying the matrix hazards. So here's an example of what a dashboard looks like in much more detail. So you can look at, you can interactively look at the microbial composition. You can interactively look at the matrix composition, and it gives additional indications such as low matrix content. And this is set up in such a way that you can input some expected species, and then the analysis comes up with the expected versus the unexpected, the proportions of the expected versus the unexpected. So again, this is really a research prototype. This is something still in the finding its way into more regular usage. But what we found was that while there is a very clear baseline of matrix, right? So you can see that the majority of samples are very near 100% in terms of the poultry meal sample, the 31 poultry meal samples we tested, very close in terms of common baseline, common composition. But there were 3 to 4 samples that are shown in the graph panel B from left to right. The first 4 samples that showed some deviations in content in terms of the matrix. So clearly, and none of this was in any, none of this was out of specification by any means, but it was highlighting that more finer differences in compositions, even at the levels of, even if these levels were below 5% of overall composition, we were able to quite reasonably identify them. And our confidence in this identification is based on benchmarking external data sets that were available in the public domain, and being able to corroborate that across multiple components, the pipeline was performing very well in terms of accurately identifying within deviation the supposed components that are in the external data set mixtures. So based on this, the additional observation we also have is that the microbiome itself has some variation due to, when the composition is varying. So we can see some very specific instances of that in some of the highlighted highlighted examples, where there are specific genera that are in a higher proportion than in the rest of the samples. So, and this is all interactive. So you can determine in how to better enhance the depiction, of course, but along with allowing us to analyze the data and allowing us more simpler but also interactive visualizations, it helps the approach helps us determine using both microbial levels and composition levels that there are deviations to the product composition, and we can use this information to determine whether or not in the future, when it's applied in a real world scenario, whether or not the material composition is acceptable. So with this approach, what we have been able to demonstrate is that we have answered many of the science questions. So we have been able to determine that metagenomics is useful. We have been able to show that, demonstrate that we can see the microbiome, we can see pathogens, we can find added organisms. So if we have altered the microbial composition, we can see it. Some of the other findings that we have and have highlighted in our publication include that the single gene approach, such as taken with PCR or 16S rRNA based metagenomic approaches, it was not adequate, and a multi-gene approach where we have better coverage by deep shotgun sequencing. We can find more numbers of species, and we have also demonstrated that matrix identification is possible. But beyond answering these questions, there are still a lot of research questions to be resolved before this moves to concept. And that is where we are today, that we are evaluating the possibility of taking the science and being able to highlight how this can be conceptually useful for the industry. But again, the research still needs to scale across the right breadth of knowledge so that this can become an actual useful operational solution that addresses many of the challenges with the non-targeting approaches that colleagues that previously have presented have identified quite extensively. So with this, we want to pause here and offer a big thanks to the organizers of the CIFSQ for offering the Mars Global Food Safety Center a wonderful opportunity to share some of our perspectives and research. And also many thanks to all my esteemed colleagues with whom we have been having some wonderful active discussions about the various approaches we are taking. And many thanks to Bert for and Maggie for coordinating the presentation events and the support they have provided us. Thank you very much.
Thank you so much, Pala. And I think since you were giving the last presentation, I might as well start off with a question to you. So we're launching into the question and answer session now. Now, what you described was like one project that is very important that Mars did, and what we observe is that there is still a hesitancy when it comes to using whole genome sequencing or next generation sequencing in the food industry. Would you be able to share your perception on why that would be? That would be helpful.
Yeah, so we have been working in this field for several years now, so we have developed some perspectives on this. I think some of the key challenges include data security as to how we would accumulate and store data. And the second is harmonization of methods, both internally and externally. So internally, in some ways, it is easier because we can build a pipeline that is consistent and uses the same method across the globe, across our operations. And that is the intention, that we want to make the same conclusions if we have very similar findings in Australia, India, China, Namibia, or Ohio, or Mexico, or Peru, or anywhere else in the world. So we don't want in different places making different conclusions if we see very similar types of data. But the other is, the widespread availability of sequencing technology is still a challenge. I think the Oxford Nanopore technology offers us a way to democratize that to a substantial extent, because we can fly someone with a kit and go do some testing someplace. But that's easier said than done, because then you need, again, the same challenge. I mean, you can go to some place and get the sequencing done, but then how do you upload the data to the place where the analytics are being done? Because some of these analytics are done in very high scale, because we are comparing our isolates to hundreds of thousands of genomes at this time. So how do you make it available? Or I mean, and even before that, sometimes even for one sample, you can generate up to a half a gigabyte to a gigabyte of data, but it's easier said than to transfer, to have as an easy solution to transfer the data in time. And I think some of these highlight some of the IT data security technical challenges. There are some operational challenges to deal with within the industry for sure, because and there are challenges in terms of understanding the landscape of, if we generate this data, how do we interact with the regulators, and how do we do this in a way that protects our business? And I think so. We had several useful conversations at CIFSQ over the past several years, where there was a more concise group of organizations present, including regulators, academia, and the industry. And I think some of the fear is fading away, because we see that, as in the past 3 years, we can see that industry is more actively publishing and sharing approaches in the public domain. And I think some of that fear is receding, though particularly in the US, if you think of operation scale, about 50% of the industry is small to medium businesses that definitely don't have the capacity to handle this type of platform. I mean, Mars can, Cargill can. I think the larger businesses can. But I think if we were looking for broader adoption, I think we need to figure out a way of democratizing this so that everybody can benefit. Again, I think, and this I think resonates with all my prior speakers at this time, that everybody is thinking on similar lines. That how do we make it available for everyone so that it's a harmonized and standardized approach? But while I think the larger organizations have a role to play in terms of helping in the harmonization, but we need to keep in consideration small to medium businesses and how they can protect their assets as well. So,
thank you, Bala. And the next question that goes also to Francois and Steve and René. I think basically starting with what you said, the democracy and the fears that are fading away. I give you an example that is somehow I find related. That is the food allergen. And here what we see is that because we until recently, because Codex now has given some reference doses that may be used by the food industry, but prior to that we did not have thresholds. So what was done was that a round table with all stakeholders, that meaning regulators, the allergic consumer groups, as well as food industry, was put together to discuss what might be appropriate levels, even though they are not fixed in the legislation. And that certainly had alleviated some of the fears of industry, but as well as consumers, to be bogged down with too much labeling or too little labeling. I was wondering if you could comment if you saw that a similar approach, especially here with the regulators, might work for alleviating further fears on the novel technologies. Now, I open that up to all the speakers.
So if I may, I will start. We have one major issue in microbiology. For many years, for the past 40 years, we always relied on the finished product testing. It was detected, non-detected. Which changed the wording in the ISO standard from absence presence to detected, non-detected. That's just seem frustrating, but it's important because sometimes people have the wrong belief. I test, I don't find anything. The global batch is safe, which is absolutely not the case. And I mentioned this example from the Estonian facility producing salmon. It was compliant with the EU regulation for testing on the finished product, but it was having an issue with its environment. It was not aware of it. So per se, on a regulatory point of view, everything was compliant, nothing bad done. But on the larger scale, it was not producing safely. And this is where we have this interpretation of the EU regulation 178/2002. That's your responsibility to ensure safe production. But the point is, how far should we go? Because we had this discussion in France following the Agona outbreak in 2017 and Puna in 2019. We don't want salmonella in the dry facilities. But if you don't want salmonella in dry facilities, you won't have a lot of dry facilities anymore, because this is microbial ecology and salmonella is naturally resistant. So we have this awareness of issue, as long, I think, as we can ensure and discuss with the authorities that things are under control, things will be fine, which turns up to a shift of mentality for food business operators. Being compliant with regulation is a must have, but it's not enough. What is important is to have good relationship with the authority, try to work in transparency, and be ready to face the issue. So this is what we trying to implement globally in this food safety culture approach, trying to be aware, raise awareness, and do something about it. So we are really shifting from just following the text to working with authorities in order to make sure that at the end of the day, we can produce, and we produce safe food, which is available for the market. And this is something that was really highlighted in this COVID-19 crisis globally over the world, is the resilience of the food supply chain and the need indeed to produce safely in agreement with all expectation from the local production to the place where you are marketing your products.
Thank you. That was a very important point, Francois. Thank you for making that. Anybody else who wants to chip in? We have Cesare and then Steve.
But I have a thought about this, what you mentioned also about allergens, because the Codex established those thresholds, but just for some allergens, the ones that are of major, that are the big 8, the most worrying ones. But across the world, we have much more allergens regulated. So even some of the allergens in the European list have no threshold at the moment. So you need always, I guess, a technical harmonization before you can put in place an effective legislation. And this is particularly true today, where the world is moving so fast from the technical progress is so fast that the legislation cannot catch up. So yeah, without a standardization, a technical standardization, I think there's no chance to do an effective legislation. And we'll also reflect on one point. For instance, in Europe, in Italy, we are very close to certain kind of innovation. We have an approach that is more, everything is not expressly allowed by the legislation, is prohibited, China, for instance, has a very different approach to many things you can see on social media, live streaming, crypto, a lot of stuff. Usually it's more permissive at the beginning, see what's going on, and notice the problems, and then jump in and regulate a new phenomenon. And this, in my opinion, it's more like it shall be in future, because the legislation simply cannot catch up with all the advancement that we are having in each field of our life, not just in food testing. And here it shall be the same. So it's very important for me to reach a technical agreement on the baseline for those methods.
Absolutely. I think Steve was next.
Thanks, Bert. Yeah, it's an interesting question. I just had a brief perspective really around the challenge with non-targeted methods, of course, is the statistics that are used and also the qualitative nature of them. They're not quantitative. And I think the community has, both for chemistry and microbiological approaches, we've seen the standards they're being used and standards exist. But I think the next step is actually having discussions at Codex level about recognition of some of these much more complex tests. And it's quite a challenge to explain them sufficiently so organizations that are like the United Nations or the FAO, World Health Organization, and Codex, can actually understand these sufficiently to start endorsing them. Thanks.
Yeah, that's a good point. Renee, you want to comment as well on that one?
Yeah, so if I understand you correctly, you would go or try to implement something like the allergen levels, but for non-targeted. But
it's more the communication, the round table, the discussion, because we are right now in a situation where we don't have fixed rules. And as Cesare pointed out, there is no legislation in place yet. So we're dealing with a new phenomenon, and we need to somehow grapple with it before legislation comes into place. That means that there needs to be a concerted action from the competent authorities, but also from the food industry and any potential other stakeholder. I think this is a key aspect. And I was wondering how you saw the involvement of the competent authorities, for example, in that context. Yeah. So if you think that would be a feasible approach.
I think it would be a feasible approach, but I know in regards to Codex, how much time this legislation takes. So 10 years, sometimes even 15 years. So of course it would be feasible, but it's also highly political. So each country has its own opinion on this topic and wants to push this agenda. So yeah, it would be really feasible if we all come together to address it, but I think it is really difficult.
It would be difficult, but I think at the same time, the approach, for example, that the AAB in Germany, the Allergy and Asthma Bund, has taken, basically getting regulators and industry and consumers around the table, that was a fairly rapid approach. And there seems to be some common understanding that we're not looking for 0.01 ppm level of allergen, but we're looking at 10 ppm level, which doesn't take people usually, unless you're super sensitive, to the hospital. So there seems to be, even outside of waiting for Codex or outside of waiting for any legislative progress, an understanding of the different groups, of the different stakeholders. So I think similar things could happen here with a non-targeted approach, because we need that. We will see at the beginning more peaks that are out of the spectrum that we have to identify, where we need to have a playbook basically in place that dictates how we should proceed. Will the authority come after us just because there is a peak that we don't see? I don't think that would be the right approach. So it would have to be a concerted action from both the authorities as well as the food industry, and that would be something that I would see, could be taken forward.
I like your provocation, Bert. I was actually going to lead to the same provocation, I think, in many ways, because I think rather than think about this on the technical terms, I think that this is an opportunity for businesses to get their intentions aligned around food safety and the larger goal of safe food for all. I think this is a very very brave opportunity. I mean, very encouraging opportunity, not brave, but encouraging opportunity for the industry to think that if technologies are overtaking the rate at which regulators can regulate, then we have an opportunity to shape what this looks like. And we have an opportunity to contribute to what this looks like in the future landscape when we start applying these various types of non-targeted technologies, be it NIR, be it next generation sequencing. Because I think, and I said this earlier in my presentation, I don't think Mars doesn't think that we're going to do this alone, that we're going to need concerted action. We're going to need intentional stakeholders getting together to resolve some of the major challenges of interpreting this type of data. And the data can be a very high quality, but again, that again needs to be aligned by intention across stakeholders, that we will set a minimum standard for data quality first, and we will set a minimum standard for the analytical platforms first before we come back and say, can we interpret this data? And I think it's a great opportunity today.
That actually brings me, thank you, Bala, for that is a perfect lead into my next question. And that is data quality and interoperability between the different analytical tools. So one of the challenges that we're facing right now is that when we're looking for non-targeted databases, no matter if it's on the NGS side or on the food chemistry side, yes, you can use some public databases, but we know that the quality of data in public databases is sometimes variable, to put it politely. So often companies own their own databases, which are well maintained, curated, high quality, but this is companies' property, so they're not sharing. So my question to all of you is, how could we at all get around the problem of sharing the data? And I remember an example of a friend of mine, Marco Lorio from Italy, the professor there. He tried to align NIR data sets generated from different tools on the same sample, and he succeeded. So because we have to bear in mind that also the technology progresses, so we will see different instruments that may generate different profiles. So would we have to regenerate these profiles, and could AI help? So I think it's all around those kind of questions. And one of the key aspects, of course, is should we have public databases that are well curated, maybe even at a state of government level or European Commission or Codex level, that would be accessible to all of us. So that means that the result that we're getting from the different analysis that we made would somehow be harmonized, similar for the bioinformatics pipeline. So what is your take on that? So
maybe I will start again, Bert. So, I mean, I think Mars would very much welcome that approach, in all honesty, because I mean, this is a wonderful provocation, I think. And I think there's why wouldn't we do that? Kind of a provocation, I think. But once we make this data public, again, there is the question of regulatory implication that we need to deal with, and the implications today are hazy at best. So releasing data into the public domain is still watched, is still listened to with a lot of trepidation within the industry, within the food industry broadly. So how do we overcome that fear? I don't know. I'm a scientist, so I developed the protocols to run the analyses, and I guide the principles by which the best juice can be squeezed out from this wonderfully big orange of genomic platforms. But to guide policy is I think it needs to evolve. I think an evolution needs to take place. Maybe Cesare or others can add a little bit more to what I'm thinking at this point.
Yeah, thank you, Bala. Yeah, I can take from there, Bert, just 1 minute.
Yeah.
If you, the legal instruments to share the data can be shaped. Of course, the most obvious solution is to send all those data to a third part that is independent, like a scientific body, under a clause that provides for anonymity of those data. Okay, you don't know that those data are coming from Mars or from another company. You just know that they had those findings doing certain kind of testing, and on those you can build your big data analysis, whatever. You can extract, extrapolate all the interesting conclusion that you can get. The problem is the fear, as you mentioned, because we speak always of food safety as something non-competitive, but most companies, sadly, I think still treat those information that they have about authenticity, safety, and so on as a competition, as a competitive advantage. Because we face the same struggles, speaking of food fraud and authenticity in Europe for the last, I think, 10 years and more. You have just to make the companies understand that in a globalized environment is for the benefit of all that you try to settle those instruments, because you can see many crises. It might be the horsemeat scandal for authenticity, now the ethylene oxide in Europe that caused thousands of recalls. If you share the data, you can get better answers all the time, and the whole sector might benefit and prevent potentially scandals and issues. But yeah, it's a long way to go, and there's a lot of persuasion and psychology that has to be applied, I guess, to get there. Thank you.
Thank you, François. Cesare, is there anybody else who wants to contribute to that point? Okay, we have François and then Steve and Renee, I believe, and also raised hand. Okay.
So I will take this from the microbiology point. When we have this implementation of WGS in the microbiology, there was this huge step forward, at least in the US, between the Center of Disease Control and the FDA to compare the database in order to make the link between clinical and food isolates. And there was tentative to globalize this worldwide. There was in the genome tracker. There's NTU Singapore proposed to be the host of all the sequence under the umbrella of Jürgen Schlunz. One of the issue we have with sharing data too fast is the education there before. As an example, with Listeria monocytogenes ST6, that's the same under whole genome sequencing. It was the same ST6 in Netherlands from ongoing outbreaks, in Hungary from the frozen corn, and in South Africa from the Polokwane outbreaks. So there is a trend right now to go too fast on the conclusion with whole genome sequence and forget that this tool is solving epidemiology. So we have to be careful that sharing data openly to people who don't have the education to understand them, it will be more counterproductive than anything else. So right now, for the past 10 years, there are this initiative starting, as Bala was mentioning. We try to be very careful, because if this initiative fails, that might be a full stop after, and then they will need supervision and make this mandatory, which is not the way forward. So yes, we should be sharing data in a way that it makes sense, it's understandable. But what is important with sharing data is we need to know who has access to the data, and make sure that they have education and the understanding to make something useful with the data. I mean, we've seen this with the COVID-19 crisis. We all share the same data, but we really see that there is a lot of misinformation based on the same data because everything is transparent. So I will take this COVID-19 crisis as an example. Sharing too openly data to uneducated person or groups of person is not a good idea. So sharing, yes, but educate first.
Very good point, François. Thank you. Steve is next, then Renee. And Bala, thank you for answering Ilka's question in writing. So Steve, over to you.
Thanks, Bert. Yeah, we've talked about the political dimensions, who owns the data and the risks, so forth. And I certainly agree that's a key part. There's actually also a technical dimension to sharing and integrating the data as well, which has got to involve the vendors of whether it's the software vendors or the instrument vendors generating the data. And obviously an understanding of the noise that's in it and what's acceptable. So some fairly upfront discussions. That's obviously proprietary to the vendors, and it's not something they want to discuss a whole lot, how the instruments perform and gather the data. So we've got to attack that end as well, or maybe attack's the wrong word, but approach it carefully in conjunction with the political aspects. That's my perspective.
Thanks, Steve. And I think Renee was last in that series. But
yeah, so I wholly agree to the things that has been said here, especially what Cesare said. And I would maybe like to expand on that from the official food control point of view. So there, as I said in my talk, especially the reference database is mostly the main challenge regarding the, for example, validation, the use of validated non-targeted methods. But there are, of course, many more questions. So, for example, regarding the access of the database, when we look at food authenticity, meaning having the database, the reference database, public, so everyone can look at it, would also mean that the adulterers would also have access to this database and could use it in theory to trick the methods. And also there are other questions regarding the legislation. For example, the Nagoya Protocol is really a difficult question regarding the creation of reference database. So there are many open points here I would like to add.
I think very good point, Renee. What I would like to respond to that one in that the fraudsters might also have access to that. The point is, I think that we will not have just one non-targeted type of method. And when we use a portfolio, it's basically what Francois said with cleaning. There needs to be a rotation of the cleaning agent used to not have one particular pathogenic strain survive and create a bigger problem. So that's the same thing with the use of methodology. There needs to be a combined or subsequent use of different types of methodology that makes it extremely difficult for fraudsters to fake all the different elements, because remember, they have to tweak something that makes the sample appear authentic. So there would be one characteristic, like the melamine with the nitrogen, where you have Kildal as the method, and they know that Kildal is being used. Therefore, they put a little bit a molecule with a high nitrogen content in there, but they wouldn't be able to fake any other property. So that would show up in NIR now. So this is why when you use a combination of technologies, even if you were to release a data set, it makes it less likely and more costly if they try to do that. I think it would become economically not more not more possible to get a cheaper sample, because the cheaper product. That would be the ultimate goal of the fraudsters, right? To make a product that has a lower quality, so lower cost. But if you have methods that look at all the different aspects, that would not be possible anymore. So I think that I'm not overly concerned. I think the legal concerns that Bala and Cesare raised, they are very valid. And Francois also mentioned, we need to educate, because you can interpret information and still provide the wrong type of information. So education and having a legal framework around the release of such databases is quite crucial in my view. But the fact that they're out in the open would not concern me as long as we have a portfolio of methods that we can apply, because process will never be able to trick all the different properties of a product to go unnoticed. So that's my personal take on it anyway. Okay, I have one more question for a lawyer. Let's assume you get a raw material in the sample reception, in the incoming goods reception area. You screen it with a non-targeted method and you get a peak that is out of spectrum. And you say, okay, I don't want that product. What could be the consequences in your relationship supplier, food manufacturer, if you did that, because you may not know what you're dealing with, and it could be just a natural variability, it could be an adulterant, it could be a food hazard. So you don't know, you just know it's a peak. So would there be any repercussion? How would you circumnavigate that situation for either supplier or the food manufacturer?
You might have repercussion, especially regarding authenticity. I had several cases where retailers were doing random testing for authenticity using non-targeted methods, and then were basically saying to their suppliers that the product was having problems, so they have to pay fines, withdrawal of the product from the shelves and so on. If you don't have any kind of contract agreement, arbitration clause on which methods you are using, what are the rules under which you are regulating your relationship, it's, you are skating on thin ice, because it depends on how you did that test. For instance, I had a very interesting case where a UK retailer was assuming that some Italian tomato was Chinese tomato. And often is not the case, because we have a lot of tomato in Italy. So the frozen tomato are less sensitive than what the public usually thinks. And we did a sampling in a very valid laboratory, all absolutely not accredited, because we're speaking of non-targeted methods. And we identified the problem in the retailer analysis, in the UK retailer analysis. And it was mostly linked to the fact that the water was disturbing the overall result of this kind of testing. So we were able to demonstrate that it was not absolutely, not just our fault, but the tomato was absolutely Italian and the analysis was flawed. So it's a technical match, okay? My expertise against your expertise. You have no legal grounds there. You just, fight on the technical data, I guess, if you want to get a restoration for damages or something like that. That's it.
Having that in a contract fix, that you say, like, okay, if a product is out of profile, I can reject it, might help, or
might at least eliminate all the objections about the validity, the theoretical validity of the methods, okay? Cannot prevent all the practical objections that you might do when you examine, the sampling, the analysis, and try to understand if they did correctly or not, and you challenge this.
Thank you, Chair. With that, we have pretty much exhausted all the questions that we had. Is there anything that any of you would like to say before we wrap up? René, yeah, go ahead.
Just a short addition to what Cesare just said. We, from the official food control point of view, we should not forget the other possibilities we have apart from the analytics to check the validity. So, for example, if it is locally produced or a local company, you can always do a site inspection of the company, or you can look at the metadata to check the traceability. So you shouldn't forget this kind of possibilities for the validity of the results to confirm.
Yeah, thank you. Very good point to remind us that the analytical part is only one aspect of, in our toolbox that we can use to ensure that a product is authentic or is safe. Very nice end to that discussion, unless there's any other comment. Bonsoir. Sure.
Yeah, just mentioning that the science is ready. We really moved forward incredibly in the past 20 years. The application is not, the implementation is not coming yet. And I think we need standardization. There are many tools available going in every direction, putting a lot of data, and regulation is based on science, but is also based on standards. So I think there is a lot of work required from the standardization body in order to provide robust evidence to establish regulation. So whenever we speak about why are we still working with culture-based microbiology and not going for molecular, it's always end up in the same points. It's not standardized, so it's difficult to interpret. So I think there is a lot of work needed. The scientists did their part. Now let's the standardization body do theirs.
Agreed. I think if I'm informed correctly, there is also some trial on non-targeted methodologies ongoing already. So we'll see the first results hopefully in the not too distant future and have the first standard. But for now, we have to be patient.
Actually, in the next generation sequencing technologies and application of technologies like Oxford Nanopore, the regulators are already investigating those types of approaches. So I don't think everybody has figured out how to use metagenomics in a regulatory scenario yet, but it's not that they're not going there, or it's not that they're not touching it. It's not that they're not investigating it. So and metagenomics is, an untargeted approach in the way sequencing works, so to speak. So I think I second what everybody else has said, and I really like Cesari's provocations earlier that, having the contract with your supplier, I think defining what you would use for identifying whether it's matching or not matching. I think that's a very important step, because with NGS data, sometimes you can get different interpretations. It's still there. So we have to, again, get some harmonization going on there.
Thank you, Bala. Well, I'm absolutely honored to have had such a fantastic panel with great presentations, with great discussions. So thank you ever so much. And we also hope that you in the room and online have enjoyed the discussion. And well, stay in touch and stay tuned. Thank you all. Bye-bye for now.
Thank you, audience.
Bye,
Thank you,
everyone.
Bert.
Thank you.
Thank you, everyone. Bye.
Bye.